indications, engine thrust and indicators, other engine system monitoring, ground running, engine operating limits, engine health monitoring, engine performance, maintenance, engine path cleaning, and some power augmentation like reheat, etc. And then eventually we'll look at basic FOD, and finally storage of gas turbine engines. So quite a lot to look through. Okay, some are quite in depth, some are quite straightforward and easy. So yeah, we'll take our time as we go through. So a lot to get through between now and Thursday. Right, so objectives again, as usual. You won't get a face test, so we're not bothered with that one. So give me some examples of indicators you might want to see in an engine. What sort of indicators might you want to see?
Yeah, exhaust gas temperature and low pressure, high pressure, RPM of the compressor blade, N1,
Yeah.
N2.
Lots of things, yeah. You've got EPR, fuel flow. Oh, there's so many things you could have a lot on. So yeah, that's just an example. What I've got here is just an example of a high bypass engine. Okay, I've got TGT or EGT, got RPM, EPR, engine pressure ratio. What was EPR again?
Engine pressure ratio, that is ratio between the exhaust and inlet.
Yeah, exhaust over the inlet. Yeah, good. Again, for the turboprop, yeah, you'd have that would be a turboprop, probably fixed turbine one. You've got temperature from both engines, your fuel flow, vibration, oil temperature, oil pressure, etc., and as many as required. Okay, some additional sensors again for EPR, IPR, JPT, jet pipe temperature, EGT, engine gas temperature, turbine gas temperature, intermediate turbine temperature. It depends on the engine. Yeah, how many you have all depends on the type, the more or less as appropriate. But we need to know stuff. The pilot needs to know what's going on. The computer system doesn't need to see the gauges because it gets the sensors straight to them. But certainly for the engineers and the pilots, we need to know what's going on because they can change very quickly. So system transmitters, indicators discussed in the following pages are just a general description. They're not specific, and they're not for any specific aircraft or engine. They're just a general oversight of what you might come across. Okay, so don't take them word for word. But yeah, your things like rotational speed, exhaust gas temperature, power, oil and fuel pressure, oil and fuel temperature. If it's got something moving in it, we need to know what's happening, basically. Fuel flow, vibration monitoring, all the good stuff. And torque monitoring as well, like a turboprop aircraft. Cool. All right, so on twin spool engines, a little example in the bottom corner here. Okay, so you've got twin spool engine, a left-hand engine, a right-hand engine, and you might have N2. There's N1, so it'll be your LP spool, your low pressure spool, and your N2 would be your high pressure. And you can see there we've got figures of 95.4 and 94.6. Okay, so just showing the speeds there. EGT, sort of 788. Oil pressure, or temperature, and some vibration as well. Again, not all, these are just examples, not all specific. So obviously your high pressure is classed as N2. Sometimes you might see a triple spool engine being classed as NH. Okay, sometimes you see that. And likewise, the LP spool, that's the first one, so N1, N for speed, 1 for first spool. And likewise, in a triple spool engine, you might see it annotated as NL. Okay, but they both mean the same. But normally for twin spool, that's how it would be annotated. Three turbine turboprop engines. Again, the gas generator is usually described as NG, speed of the gas generator, so NG for that one. So again, a few more abbreviations. And your free turbine, the power time, is usually referred to as NF, okay, for free turbine. Engine speed indication shown by actual revolutions per minute, or by as a percentage of the maximum engine speed. Okay, so in this case, we've got 95.4% and 94.6% of the total engine speed. Otherwise, certainly turboprops, it might just be revs per minute times 100 and times 1,000. So, reference to speed, we're going to look at a thing what's called a tacho generator. Basically, this is your speed gauge, lets you know how fast your engine's going. Okay, now a tachogeny shorthand we call it tachometer generator. Okay, what it is, it's a miniature three-phase delta wound, commonly known as a squirrel cage. You would have heard of that possibly in Module 3, basic electronics. Permanent magnet rotor alternator, which is connected to the engine. Okay, basically an AC supply. The frequency of the three-phase output is proportional to the engine speed. So it's a good one to note there. Again, if you get asked a question, frequency of the tachogeny, is it proportional to engine speed? Yes, it is. Okay, it's a good one to highlight there. Back a minute. Okay. All right. That's stuck. Where's that stuck? Try again. Right. Okay, so tachogeny, the generator which supplies the power to the actual motor. Okay. We've got basically fitted into the gearbox. So get on there. There's your drive shaft. Okay, into your gearbox. There's your permanent magnet. So your three-phase squirrel wound. Okay, so your permanent magnet generator there. So that provides the actual pulse or the power to your actual rotor, which will connect then to your actual indicator. So you've got a motor that supplies the power, and that supplies the power to your indicator. We'll look at how that works in a minute. So again, three-phase delta wound squirrel cage magnet, and I said it is proportional to engine speed. So the motor supplies the power, then you've got the indicator, okay, and that's a synchronous indicator there. This is the type of thing you might come across. We're not looking. You see, it's got reduction gears in there as well, springs, and your flux coupling, synchronous motor field. So it's a magnet rotating inside it, and it'll have a drag cup and a few bits and pieces. But at the end of the day, you have a big pointer and a small pointer. Okay, and we'll look at that just in a minute. So there's your motor. Okay, generator itself connected to your indicator. So again, that'll be attached to the gearbox. Okay, then that'll supply the power to your actual indicator. Now, the indicator is similar again because you've got a three-phase generator. So this time you've got a three-phase motor, synchronous motor fed from the output of your generator. So it's all three-phase. Synchronous motor rotates proportionally to the speed of the generator. Yep, and that obviously gives you the correct speed of the engine. It's entirely dependent upon the frequency that's fed to it. So the greater the frequency, the greater the indication. Synchronous motor of the indicator is coupled to a permanent magnet, drag cup assembly, and a control spring, and then to the pointer and the indicator. Okay, so basically what you've got here is a 10-to-1 reduction gearing. All right, so for every one revolution of the, in other words, you can call it the crankshaft, the indicator will rotate one. So you have your 100 RPM pointer and your 1000 RPM pointer. So the big pointer will go around once, 10 times to your 101. Now the 4-pole magnet in there, you've got a drag cup. So basically, actually inducing a pulse, it's trying to drag this cup round with it. But because we've got a little spring there that resists that, so the faster that goes, the faster that will try and move the cup. And the cup is obviously geared to the tension on the spring. And the more that spins round, because the magnet doesn't touch this cup at all, it's rotating in it. Because the magnet is also trying to touch it, it tries to pull the cup round. And it has to get to a certain revolution before it actually starts spinning the cup. And the tension spring just is calibrated to maintain that tension, because otherwise it'll be too fast and you get a false indication. So hence why the calibration from the cup and the spring and the reduction gyro gives you actual indication. Okay, and it's always a 10-to-1 reduction gearing on there. Okay, so this shaft here will be rotating 10 times to give you an indication on your the actual indicator itself. Okay, so your 2 pointers are 100 RPM pointer and 1000 RPM pointer. Okay, so the big one is going round 10 times as fast as the small one. So for every 10 that goes round, that'll be 1000, 2000, 3000. Yeah. All right, so that's the basic tachogeny tacho indicator. So 3-phase squirrel cage for the motor and a drag cup, 10-to-1 reduction gearing for the indicator. Okay, put this pointer back again. Anything else on that one? No, that's fine. Oh, that's fine. Any questions on that one? I'll just make sure I haven't missed anything there. Okay. More in depth on module 3, but you don't need to go that deep on module 15. So another type of sensor we've got for speed is a phonic wheel. A phonic wheel is a lot of modern cars and lorries and even some new motorbikes have ABS on them. And what it is, it's a sensor that's inside your hub, your wheel. And as the drive shaft is rotating round, you'll get a pulse from a tooth that is in the actual wheel as well. And that's how ABS systems get the signal. So the probe consists in this case of 2 permanent magnets, 3 pole pieces. So you can just say there, little dot there, and dot. So it's 3 pole pieces. Okay, 2 permanent magnets and a coil assembly to pick up the power as you get the induction of the magnetic field. The spacing of the pole pieces is equal to the pitch of the teeth on the phonic wheel, which is what we call integral to part of the N1 and N2 shafts. In other words, the N1 shafts, N2 shafts are machined to have a tooth cut out on them. So this would be your N1 or N2 shaft, all right? And there's your tooth, so you've had a bit of cut out. Basically looks like a spur gear type thing that's been cut out of the shaft. So the shaft will be rotating, and as it passes the pole pieces, okay, you've got a coil on one of them, that will give you a positive and negative direction, induce a magnetic field, which will then induce a voltage. And that'll go through an amplifier as well. Okay. Again, variable reluctance type design, interact with teeth of the wheel and determine the rotational speed of the shaft. All right. So again, the faster the shaft's rotating, the faster the pulse, the faster the indication. So this is one we want to look at. This is a diagram that's in your books. You can see there's your speed probe, number 2 probe, number 1 probe. We'll come on to why they're slightly out of synchronization in a minute. You might have two probes to give it a feedback, but they're also mounted 90 degrees apart, which allows us to tell if the shaft is spinning in the right direction. Those are 90 degrees apart. If that angle changes, okay, it's going the wrong direction, we get a negative sort of feedback. So we'll get a false, and what should happen therefore is the engine should not be allowed to start until it's rotating the correct way. Because if you've got an engine rotating the wrong way and you try to start it on the starter motor, that's going to put a lot of strain on the starter motor. And there was once I was flying from London and just happened to be beside the window where you could see the engine. I was just looking at the window and I saw the engine was spinning really, really fast. It wasn't started yet. It was a very windy day. It was actually spinning the wrong way, but it was really, really fast. I went, oh, it's not right. So eventually they went to start the engine and the engine went like that and just went, stopped dead quick and then went the correct way, which wasn't very good. So I think a poor engineer might have been changing a starter motor possibly later on. Okay, right, so 2 sensors, 90 degrees apart for showing you direction of rotation. Again, you'll induce the faster you move through a coil, the more volts you get positive volts, negative volts. So let's look at the first one here. So there's the top of the tooth on the wheel, which would be that part there, yeah? We've got the magnet, got the 0 volts position at the moment. Now we've got rotation of the crankshaft going towards this direction, yeah? So at the moment we're at the top of the tooth and directly above the sensor. So if we get that indication, that position, we will get a 0 volts indication, okay? So directly above the sensor, we get 0 volts. We also get 0 volts when it's at the bottom, or I call it the valley, the bit in between the teeth. So either directly in front of the sensor or directly opposite at the bottom of the tooth. Okay, we get 2 0 volt positions. When we're going down the side of the tooth, or down at the valleys, I call it going for a ski trip, okay, that's max negative. You're going down the way, so that's maximum negative volts. And then we're going back up the tooth. Okay, well, that's positive. We're going back up the way, so that's positive. So we get max positive volts. You'll start directly off the tooth, 0 volts. Start to go down the tooth because the tooth is moving away from the sensor. So it will only start seeing some of it. So we get negative, max negative, and then 0 volts. Come back up to max positive, and then finish again on, so max 0 there, and finish on max positive. Okay. So the question you get asked is, if a sensor is directly opposite a tooth, which could be this one, or it's directly opposite the gully or the bottom, the valley of the tooth, the land as we call it, then you'll get 2 0 positions. So it's always 0, max negative, 0, max positive, and then back to 0 again. Okay. So we'll just go through that once more. So 0 volts, 0 volts, going down the hill, max negative, so going down the way, going back up, it's max positive. Okay, that's all you need to remember from that one. Just to highlight that one again, having 2 sensors 90 degrees apart, should that angle change because of the way it's moving backward, we'll get a negative reading, so that will tell the system that the spool is rotating the wrong way. If it's rotating the wrong way, it should not allow the engine to start until it's rotating the correct way. That's why they're positioned 90 degrees apart. Okay. Likewise, you can see there, there's another sensor, and again, there's a bit of indication of the teeth on the shaft. Okay, so as it's going the right way, that's fine. Get direction of rotation. So I said 2 speed probes used are out of phase with each other at 90 degrees apart. Now you might have another one which we use for what's called averaging. Okay, so you have an LP speed probe, okay, for N1 and an N2 connector there. So there's your 2 probes, very close together. That helps you provide the direction of rotation. Just on that one, if I just double check, I think that's the one I was on about. Let's see. Yeah, that was just the one I was just double checking. We're having the 2 there, we're having the direction of rotation. Having 2 will allow you to determine that the engine is actually rotating. Now, some aircraft will have a light that might flash to let you know you're starting, or a flash, or won't come on at all to let you know. Well, it will come on, that's in the wrong rotation, it's going the wrong way. So again, the system, your ignition system should not work until the engine is going the right way. Like the aircraft I was on, it just suddenly stopped. The starter motor basically went to start it. Because the engine's going the wrong way, it just stopped it spinning the wrong way, and it didn't even look right. I thought, oh, that's going to put a bit of damage. So ideally, if you're going to start an engine on the ground as an engineer and you see the engine going the wrong way, what we used to do is an old trick. We get a big bin lid and put it at the back of the exhaust so the air could not flow through it. That would slow the engine down, and once it stopped, then we go for an engine start. But the best thing is obviously when you go for an engine start on the ground, is where possible, always have the aircraft heading into the wind. If it's heading into the wind, then it will rotate the right direction. But again, if it's really windy day, it could be too fast. Even though it's going the right direction, that might be too fast. So you have to be very careful. Now, fan blade, speed and direction and rotation sensor. Okay, again, just an example there. So there you go, fan blade speed and direction. So you can get combined versions. You've got signal conditioner, there's the case, there's the head, you'll get a magnetic field. And again, if it's going the right way, it'll give you the right rotation as well. Example. Okay, right, other things we'll look at. Just show the right page. Yeah, pyrometry system. What do you think we mean by pyrometry system? The clues in the picture.
Exhaust?
Not just exhaust. Where's it going to be really hot? Apart from the exhaust.
Combustion chamber.
Yeah, combustion, and especially the turbine. We need to check certainly definitely need to check the heat of the exhaust, need to check the heat of the turbine and potentially the combustion chamber, but definitely exhaust, because that's the limiting factor. The heat coming out of the exhaust, we know what's happening there. If it's too hot, we can't put more fuel in, because if you put more fuel in, that'll make it too hot. So it tasks the gas turbine engine, produce energy-rich air that can be passed high velocity onto the turbine. And the hotter we can get that, or the hotter we can get the turbine, the NGVs to go, then the more efficient that'll become. But we need to be able to sense the temperature coming out of this. We use what's called pyrometry systems. So thermocouples, these are the sensors that will actually sense the temperature in the engine. And a thermocouple is basically two lengths of dissimilar metals joined together at both ends and form a loop or a continuous circuit. Okay, one of the junctions is heated. That'll be where the actual gas coming out of the engine. And that will make an electromagnetic force, or EMF. When you heat a metal, two dissimilar metals, you produce an EMF, and that will generate a circuit. Now, the magnitude or how much of that EMF will depend upon the combination of metals that have been used and the difference in temperature between the hot and cold junctions of the metals. Now, the hot junction is the tip of the thermocouple. It's actually in the gas stream. The cold junction is the aircraft side, where we'll induce a small voltage. So the hot junction is being called the reference point, the bit of the probe that is sitting in the gas stream, which is getting heated up. And that effect is used to measure temperature, especially in the higher ranges. Okay. The heated junction, again, is known as the thermocouple, and placed in the point where the temperature is to be measured. In our case, it'd be the exhaust gas coming out. And another junction said the cold junction computed by millivolt. So millivolts, very small voltage, just enough to give a little flow of power. So again, with the change in resistance of the thermocouple on two dissimilar metals, you'll get a circuit going round. Again, the voltage will change, and that will go through an amplifier, which will go to a gauge, and also your fuel control system. So again, that measures EMF produced and measures in terms of temperature. And this is known as what's called the Seebeck effect. Okay, the Seebeck effect is a phenomenon where temperature difference between two dissimilar metals, or electrical conductors or semiconductors, produce a voltage difference between the substances. Okay, therefore, if you've got a small millivolt going through, depending on the resistance change, depends on the amount of flow, which will increase or decrease the current. Okay, so known as the Seebeck effect. So there's a typical thermocouple harness. So you've got the thermocouples themselves, the probes. Okay, it depends how much in the aircraft. You've got what go there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is pretty much standard. We do have thermocouples in the old engines. Some you will have them in the new engines as well, but we have a newer system which we'll come on to shortly. But most of the standard engines will have thermocouples at the back. But as you'll find out shortly, they're only good up to a certain temperature, which we'll just cover. Your connections, you have two wires, usually red and blue. Blue for your cold junction, red for your hot junction, and then you have a connecting plug, okay, to make the circuit. All right. They're very, very sensitive, as you'll see as we move through the actual setup. So thermocouples, there are two types of thermocouples common in use. And the two types you want to remember or highlight is the first one is a stagnation type, and the second one is a rapid response type. And they do what they sound. So stagnation type. Stagnation. So if you see this diagram here, we've got the tip of the probe. Okay, this is about there's the exhaust gas coming in. Now the reason it's called stagnation is you have a big hole down here, which the gas goes in, then comes through, then goes out to a smaller hole at the back of the thermocouple. And because they're not in line, they're staggered. That's why it's called a stagnation thermocouple. All right. So that's a stagnation one. Your rapid response one, now, is they have the same type of holes, same size of holes, pretty much in line. So when it comes out, it spins about and then goes out very quickly. Now there's pros and cons of both of these. The stagnation one is slower because it comes in quite quick, slows down and slow to go out. So it's more accurate. Okay. The rapid response one, as it sounds, is quicker, but it doesn't stay as long, so it's not as accurate. So you want more accurate in certain engines. A rapid response one, you just want maybe like a cooker and that sort of thing. And you get variations of these. There's your couple. So you got your red and your blue. So you have your hot junction and your cold junction, which will be the cold one will be supplying the millivolts. Again, your two dissimilar metals, some sort of insulator, and you don't want to give spurious readings, okay, for both of them. So they both have the sensors in there, but it's how the gas goes in and how the gas goes out determines the type of thermocouple. So stagnation, the holes are staggered, and rapid response, the holes are in line at front and back. That's the main difference between the two. And you might have one with 2 or 3 thermocouple elements in it. Normally it's just 2, but you may indeed have 3. Okay. So that's the main ones: stagnation and rapid response. Okay. There's a basic circuit for them. All right. So the junction box is your flight deck gauge, and we're going to look at resistors and electrical connections in a minute, but that's just a basic circuit which we'll have on them. Some of what's made is nickel chromium and nickel aluminum. Some of the Americans got aluminum, that's aluminium. So nickel chromium and nickel aluminium is usually the type of materials we use in them. And we're going to look at things called ballast resistors and trim resistors just shortly. But that's just a basic layout of a thermocouple system. So the indicator, again, basic form of indicator is a moving coil millivolt. So again, millivolts responds to the EMF produced by the thermocouple. Again, change exhaust gas temperature, and we'll move your pointer accordingly. Yeah, so move it accordingly. So it'll be 100 degrees, 300 degrees, 500, 700, too hot. Right. Compensation for changes in a cold junction, an indicator temperature is affected by a few different things. You can have a bimetallic spring, or by feeding intake temperature, T1, into the system via another thermocouple sensitive to lower temperatures as well. Okay, so we've got to compensate for different temperatures. If you discount the gauge, that will cause it to indicate the ambient temperature at that time. And this thermocouple is normally made of iron and constantan, which is a copper nickel base. So T1 thermocouple, not the thermocouple exhaust, but the T1 thermocouple. Okay. In fact, I'll just go back a minute because I want to make sure I've got that there for you. I'm sure it was there. No, I'll come back to that in a minute. Okay. The T1 thermocouple normally made of iron and constant. The resistors we've got in there, we need to put some resistors in there just to allocate for different engines and different aircraft. Some aircraft have 2 engines, some aircraft 4 engines. So if you've got all the same type of system fitted, and theoretically each system, the pyrometry system for each engine should be exactly the same, but they're not. Now there's 2 resistors we're going to look at. The first one is the ballast resistor, and the ballast resistor is fitted to ensure that we get the engines all read the same on the indicator. Now they won't be all technically the same on each engine, but the pilot just wants to say, let's say the reading, for instance, maximum thrust is 600 degrees. Okay, well the pilot doesn't want to see 4 gauges, one engine reading 598, or one engine reading 601, and one engine reading 597, and and that sort of thing. He just wants to see 4 gauges, maximum throttle, 600 degrees. Okay, that lets him know that all engines are working correctly as well. The actual temperature will vary for each engine, but the ballast resistor compensates for that. Now they'll be specific to each engine, and they can only be adjusted prior to the engine being delivered to the aircraft. So this will be done in an engine bay. Normally, you wouldn't change it in situ. This will be done in an engine bay because it has to go in a test rig, test facility, and then they can tweak it to give the engine to the aircraft ready to fit. All right. So ballast resistor, think of ballast as balancing. In other words, balancing all the gauges to read the same, especially on a 4 engine aircraft. All right. Next one is a trimming resistor. Again, indicators and controls are made to be size standard. Now, the trim resistor, it allows for discrepancies within the materials of the components of that system. And what I mean by that is every engine will have wires that go around to thermocouples. They will have all the same type of thermocouples or the same set of power system. So you think in theory it should be the same. But what changes? Well, metal changes with age. Some of those thermocouples might be new. Some of the thermocouples might be old. So the resistance values in there will be different. So the trim resistors allows to calibrate that all the different components on the engine. Okay, so different resistance, each system will affect the calibration. So it trims for calibration of control to help control the fuel flow. So compensate for small variance in system resistance, they fit to either the engine or the airframe thermometry system, and sometimes both. One of the trim resistors using the airframe will be adjustable to allow for small variations to be compensated for. So it's the material properties of the components, the harnesses, the connection, and even if you torque tighten it too much or not enough, that can change the resistance properties as well. So again, the trim resistor and the balance resistor will be fitted by a test bay, okay, facility prior to the engine being delivered for the aircraft. Averaging, sometimes you need to get an average of temperature within a certain point, and there will be several thermocouples placed in the gas stream at one point, but each thermocouple will be a different length. And what I mean by that is, if you look at this diagram here, we've got a long thermocouple and we've got a short thermocouple. Now, the long thermocouple will sense the slower gas stream because the slower gas stream will be in the center of the spool, whereas the faster gas stream will be towards the outside of the tips. Yeah, it's going faster. So comparing the two temperatures of the gas, it doesn't seem much, can't be much of a distance, and that will give you an average reading. Okay, so a double element type there. Okay. And then we'll move on to what's called optical pyrometers. Now, an optical pyrometer is far more sophisticated, far more accurate than a thermocouple. Now, thermocouples are only good, and good to make a note of this, are only good up to 1100 degrees Celsius. Okay, anything above that, they break down, that they can't really cope with the heat above that. So as we've got newer engines, hotter engines, well, these type of systems became redundant. In fact, they weren't any good anymore. They weren't as accurate with the high performance engines. So you tend to find these on the older engines, but they'll still be fitted as a backup. Okay, but pyrometer systems use high engine temperatures, again, in modern turbine engines. The reason that is because turbine engines can now be nearly 1500 degrees or even hotter. Now, this is probably slightly old, but at least 1500 degrees. So a thermocouple, if it's only good up to 1100, when it comes to the turbine temperatures of 1500, it's not good. So we have to use a slightly different system. And basically what it is, it looks at the heat of the turbine blades. Okay, when you heat something up, you give a light source. The energy from the heat is infrared light. It is sighted on, now the sensor is sighted onto the turbine blades of the tube and is focused with what's called a photovoltaic cell. Okay, so this photovoltaic cell through a lens. So here we have, there's a cell here. Then the lens will put the image onto the cell. The process of a photovoltaic cell, think of a solar panel. We get light from the sun and we're using a photovoltaic cell and convert that to electricity. Well, this type of system does exactly the same thing. It converts the infrared wavelength. Depending on how intensive that is, will then go to an amplifier. Amplifier will amplify that signal and send a signal to your fuel system and also to a gauge as well. And this is sort of systems that we used to use when I was in the military and the Air Force. And to be honest, commercial aircraft, commercial engines nowadays pretty much have this type of sensor. Very, very accurate. And as you imagine, the good old hot turbine blade is almost glowing, yeah? So the hotter it gets, the greater intensity of the light, the greater the wavelength, the greater the frequency, and so on. So basically, as I said before, the cell converts the infrared radiation into electrical voltage, and then the pyrometric system will convert that into the fuel system, which will, depend on selection of the pilot, allow more fuel or decrease fuel accordingly. Early symptoms of this one, or sorry, early versions of this one, there's an opening there, okay? Because we need to have an opening to let it look into the turbine. Well, the initial ones, there's a lot of carbon buildup on the outside of these, and we'd have to take them out every so many hours and do what was called a clean and cal. Actually clean the pyrometer lens, special cloth, then we put it into a special radiation source and actually induce a pretend radiation wavelength, and we would calibrate the pyrometer to make sure it was within limits. And then once we cleaned it, it was okay, we put it back in to there. The newer ones, they now have a little, what's called a shroud that extends slightly further. So what that helps do is induce, because you've got the fast moving gas flowing over it, it pulls all the high pressure from inside the pyrometer itself. So that stops the carbon building up. Occasionally they do carbon up, you have to clean them. And even with the early ones, they were screw-on types, and they found that eventually these parts would unscrew themselves and fall off into the turbine, which was not very good. So what they did, they put a little locking tab on it as well. Very clever, very sensitive, and far more accurate than a normal thermocouple. So that's an optical pyrometer using a photovoltaic cell. Okay, so there's your lines. And there's a typical one. So a braided lead, okay, again, because you're producing a signal, it helps protect it in the engine bay as well, and then give any false signals to anything else as well. And normally you have at least two of these, probably just above each other. So one slightly higher, one slightly lower, and that gives you an average. Certainly the ones I used to work on, we had two of these, and they look very, very similar to there. You've got a screw head at one end, so you locate the pyrometer into the actual assembly, and you can't quite see it here, but it's a serrated type setting, so it locates it in. And then there's a threaded portion there, and this long part here would thread down and actually lock tight the pyrometer into place. Then what you would do, you would wire lock that one to the other one, and that would keep it in place as well. Okay, so that's your basic pyrometry thermocouple system. Thinking of that note, let's go for another break. We're going to look at engine thrust and indicators after this one. Any questions? Metals, due to the heat of the gas, will cause that electromagnetic force, and then because of those two dissimilar metals and the change in resistance, we call that Seebeck effect, and that will increase or decrease the voltage and also increase or decrease the current as well, which will give a little millivoltage supply up to your amplifier. Amplifier will increase that so you can actually use it on a gauge, and some of it might go to a gauge and some of it might go to the control system, the fuel control system. Okay, and typically you'll have the voltage supply. There's only about 25, that's called a millivolt, it's only about 25 millivolts. Okay, I forgot to put that on the slide, just a note in the book. 25 millivolts at roughly 600 degrees C difference between the hot and cold junction. Okay, again, I'll cover that again later. I will put it on the PowerPoint when we get a chance. What are the two types of thermocouples? What was the names of them? Two types of thermocouples. Yeah.
Yeah.
Which one was slow and accurate? Yeah. So the big hole that is facing into the gas stream and the small hole at the back of the probe. So it comes in, goes up and then out. So that's why the holes are staggered. Hence the stagnation name. And the other one's rapid response, which is quicker. Because it's going in quicker and coming out quicker, it's not as accurate. So there's positives and negatives for each type of one. So stagnation is slower, more accurate. The rapid response is quicker, but less accurate. Okay. Okay. Let's see. Yeah, that's that one. Right. For changes in conditions like a cold junction, change cold junction, temperature is affected either by a bimetallic string or feeding intake temperature T1 in the system from another thermocouple. Now, the thermocouple in a T1 is normally made from what type of material? Yeah, iron and constantan. Good. A ballast resistor. What is the purpose of a ballast resistor?
It's to read the same temperature.
Yeah, so a given thrust setting, all the indicators for each engine will read the same temperature. So balancing out indicators. Okay, good. And what is the purpose of a trimming resistor? What's the purpose of a trimming resistor?
It controls the amplifiers.
Not control amplifiers. What does a trim resistor account for? Now, every trim resistor on each engine will be slightly different. Same as the ballast resistors, they'll be calibrated for that specific engine to do the same job. But the ballast resistor did the balancing for indication. The trim resistor
To compensate for a small variation in the system resistance.
Yeah, the different resistance, although they have the same components, the same harnesses, the same thermocouples, some will be older, some will be newer. Materials wear down, resistance balance. So the trim resistor, the key word is calibrates for the differences in or the variances in resistance of each of those components. Okay. Averaging. We might have two thermocouples, two different lengths, and that gives us an average. Yeah, in the book, again, I'll read it out to you. Some systems will sample temperature different readings at frequent intervals so that the fatigue levels, which is low cycle fatigue, because a jet engine works on a low cycle principle, because we start an engine up, it'll run for so long, and then we'll shut it down. The difference between low cycle and high cycle is if I get a light switch and I go click, 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 off on, off on, off on, off on, that's high cyclic fatigue. In other words, I'm going to wear that switch out very quickly. If I switch a light on and leave it for a few hours and then switch it off, that's classed as low cycle fatigue. And a jet engine is the same. A piston engine is high cycle fatigue, it's going bang, 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 yeah? Whereas a gas turbine engine is low cycle fatigue because it is, we'll get high cycle stresses for the turbines, but for generally we start an engine up, it stays started, and we just add more fuel as we go along. So we class that as low cycle fatigue. Other thing I want to add there, in all cases, commercial aircraft, a thermocouple output will also be passed to your ADR, your accident or aircraft data recorder, okay, your little black box. So all temperature readings, just in case there's a problem with the aircraft, it crashes or whatever, any information the engine gives out, speed, temperature, fuel flow and all that stuff, that will also go back to your ADR. And it's every few fractions of a second. Okay, just what I meant to highlight there as well. And it helps give diagnostics in case there's been an accident. Okay, what temperature does a standard thermocouple sort of go up to? What's the maximum range of a standard thermocouple? Yeah, 11 degrees. But turbines can be in excess of what temperature?
600 degree, 600.
Well, more than that.
600.
1500.
1500 degrees, yeah. You think about the thermocouple is an exhaust gas, so if you come back the way to the turbine, it's got to get hotter, yeah? But the combustion system is about 2000 degrees, the turbine's roughly 15, maybe 1700 degrees. So we need a better system to take the temperature, more accurate temperature, especially for the NGVs and the turbine blades. So we use the pyrometer. And what was the basic principle of a pyrometer? How did that work?
The photovoltaic cell.
Yeah, a photovoltaic cell, that's the name of it, yeah. So the cell will convert the infrared radiation wavelength into an electrical signal. And again, that'll go to an amplifier, be amplified to a gauge sensor and also to your fuel system. So the fuel system needs to know, okay, what temperature am I at? Can I give more fuel? Can I not? And also indication as well. Okay. On the early models of pyrometer, they're very prone to getting lots of carbon on there. So how did they fix that? What sort of modification did they put on it? Yeah, it basically allowed the fast-moving gas. If that's fast-moving, it must be low pressure. So any still gas that's in the adapter, that's going to be high pressure. So high pressure winds goes out into the screen, yeah. So it keeps the carbon away from it. Good. Good, good, good. Okay, that's pretty much it for there. Any other questions on what we've covered so far? I'm just double checking a few bits there, make sure it's the main one. Yeah, I've covered that, that's fine. That's pretty much the main parts you want to highlight or remember. Again, some stuff wasn't in the PowerPoint, but I've just gone through it in the book. Any questions you have about what we've covered there so far? All good? Right, fantastic. Okay, we'll do a little start on the next section. We won't too far, it's almost food time. Getting hungry. All right, so we'll have a little look at thrust, engine thrust and indicators. Okay. Oops. Right, okay, so that was parametric systems. Again, we will recap that at probably end of today as well. So now we're going to look at engine thrust and indicators. Now remember, where is thrust felt in an engine? Where do we feel thrust in an engine?
All rotating part out, static part.
Yeah, all rotating and static, and also forward and rearwards as well. We get thrust going forwards with the back pressure, but also we get thrust coming at the back one as well. And then because we've got thrust going forwards, thrust going backwards, we take the less of that. And in this case, just a little example, we've got a gross thrust of 57,000 and about 46,000 going back away. So overall, this engine's producing about 11,000 pounds of thrust. Okay, and you can see where it's split up into the base. This is just an example. Again, it's just not perfect, just a little example there. Okay, so we're going to look at this. Just change that. Oh no, don't want that one. There we go. Okay, yeah, so good. Thrust is always static and rotating, but also forward and back. No, we need to know what's happening on the gauge, how much thrust producing, and how much thrust we might require for takeoff, different airports, different altitudes. We can actually set how much thrust we need. It's fine if you've got a long runway. Some runways are very short, some runways are at higher altitude, so we need to make sure we've got the right thrust available, depending on the weight of the aircraft and the load, etc. So we'll use what's called a DPI, a direct pressure indicator, and this displays the turbine outlet pressure only. Okay. And this gauge is set by turning, that's not the best diagram, but it's turning the little dial there, or knob, at the instrument to set what's called an index number. Now the index number, this will be calculated from a graph in the pilot's book, or engineer's book, usually set in inches of mercury, is referenced to the chart, normally set in millibars. So we can set that by turning this knob here, we can set this arrow which will go around, and that will tell us that's the thrust we need. So when we put the throttle forward, we can put the throttle forward to match the thrust we need to take off. Now remember, you don't always need maximum thrust. You might just set it to thrust available. Likewise, if it's a short runway, you might need all the thrust available. But on certain days, a nice, cool, dry day, you'll get more thrust available, so you can take off a bit shorter. On a hot day, same runway, yes, you're going to need more thrust because there's less oxygen. So you can set this dial to tell you how much thrust you need once you've calculated using the reference. Because if you just start an engine up and you've got any calculations, how much fuel you've got on board, how much cargo, passengers, and you just go full throttle, you might or might not take off. Yeah, there are some occasions where aircraft have been so full, the day has been that hot, the aircraft cannot take off. It wouldn't have a long enough runway, so they've had to wait till cooler temperatures to get the thrust available. Okay, and you'll check as an engineer, you'll check that when you're doing ground runs. You'll check the thrust available specific from the temperature you've been given by air traffic or checking outside, checking against the graph, and it should tell you should have this amount of thrust available. So index number, as I said, is referenced from a pressure and temperature chart specific to that day. So today might be 10 degrees, tomorrow it might be 15 degrees, the next day it might be 5 degrees. So again, those different temperatures, according to the graph, will let you know how much thrust you should be able to get depending on your engine type. So to set it, you just simply turn that little dial there, and then that will tell you how much thrust. And that's what we call indexing. Okay. Again, usually expressed in millibars and temperature in degrees as possible. Only effective at certain forward speeds, as they do not allow for ram effect. Yeah, so remember, ram effect is the air getting rammed in intake. So as intake pressure increases, well then fuel mixture thrust will also increase as well. So again, it's only specific to certain aircraft forward speeds. Again, that will be in the graph to check with. Specific charts to cater for engines located in different positions on the aircraft. And furthermore, index will have to be adjusted for anti-icing, where you have anti-icing on or off. Because remember, if you have anti-icing on, that can potentially decrease thrust. Now, if you're in a cold, slushy day, you might have to have anti-icing on. You might not be able to take off because you've got that on. So again, you have to refer to the chart. Apologise for that covering there, but the chart's in your book. Again, it's not clear here, but you would use that as a reference anyway. So I said there, the graph will be in the maintenance manual or the flight manual. And again, the 3 PIs are only affected up to certain forward speed. And it does say roughly about 50 knots, since they don't compensate for ram effect. Let me change that little diagram there. Okay, so if in doubt, check the manual. Have you got anti-icing on? Have you got off? Will your aircraft take off? Will it be able to take off? So again, very crucial, obviously. So yeah, oh, that's one. I'll just, while I forget, guys, so I'll go back and get rid of that one because I know what's happened there. If I don't do it now, I'll probably forget. Give me 2 seconds. I'll just get rid of that. It's not tea break, don't worry, just hang on. I'll get back to that one. Where's it gone? Where's it gone? Where's it gone? Where's it gone? Right. Okay, let's get back to it. There we go. Right, so that should work now. There we go. That's better. Right, so I've moved that one. Apologies there. Right, so yeah, up to about 50 knots. Engine pressure ratio, which is obviously exhaust over intake. So the greatest ratio that will be achievable is when the aircraft is static. Now, the reason being is you're static, you're on the ground, that's going to be the highest density of air available. Because the higher you go in altitude, obviously pressure decreases, therefore you're going to have to go faster to get ram effective air into intake to make up for that pressure. So the greatest ratio will only be available when the aircraft is static and the engine is operating at maximum fuel flow available for the ambient conditions, depending on temperature of the day. So good one to note there. As I said before, EPR is simply the exhaust pressure, okay, over the inlet pressure. So exhaust over compressed inlet equals EPR. All right, that one there. So engine pressure ratio, because engines drawing in air from the surrounding area, thereby creating the depression in P1 from the intake. So in order to promote maximum available both hot and cold stream of a fan engine are choked, we mix those together, and the back pressure from this is giving pressure thrust. So we get pressure thrust to exhaust across the nozzles and the reading at exhaust. So PX just stands for pressure exhaust. Okay, so that's the back pressure. You're creating pressure thrust from a choked condition, like we saw a few days ago. That's your pressure ratio. So the comparison between intake and exhaust, therefore, as we said already, EPR, or engine pressure ratio. And we use it to measure the thrust that an engine is developing. And it can be used for off-flight ranges as well as on the ground. And it's very useful for setting the throttle levers for both economical engine running and also for maximum takeoff settings. In other words, we can set the thrust available. We might need all the thrust, depending on the type of day it is, or we might need not quite as much. Might just have to set the throttles to maybe 90% of thrust. Pressure ratio from the engine at any given time can be discovered again by consulting the graph or by looking at a computer on the flight deck. Most of the modern ones now, your ICAS system and that sort of thing, ECAM, it's all digital, it's all on computer, ready to go. Pilot and yourself will input temperature and pressure of the day, and that'll be able to calculate what your thrust should be against the engine's graph as well. So in each case, it may be possible to discover the recommended EPR for 3 things you want to remember here is climb, go round, and takeoff. So yeah, you definitely need to know what thrust you've got available for takeoff. You might need to go around for go round, so you come into land, but you actually need to go off and go round again. How much thrust you've got for climb, again, that will change as you increase altitude. So by inputting and consulting a graph, you'll be able to tell if you've got, say there's an airport that, it's one near Japan, I think it is, they've got the high mountains. Even Nepal, you've got obviously the high mountains there. Have you got enough thrust to take off and actually clear the mountain? Okay. Best calculate on the ground before you go flying, because that could cause problems. Once you've been informed of EPR for that situation, you've calculated the pressure thrust available, the pilot will now what's called bug the gauge. Okay, so basically set the gauge and set the throttle levers to the limit indicated on the gauge by the bug. And we set the needle. So when he's putting the throttles up, you will see the thrust gauge go up. And once he gets to his power rating, if the needle doesn't get to where it should be, then he will have to make a decision that I can't take off, or yes, I can take off. All right. Normally, an EPR reading at full throttle setting on the ground would be around 1.6 to 1, while at idle, the reading would be around 1.07 to 1. Okay. All right, so we'll leave that there for now. I think it's time to go for some food. I think everybody happy to do that? And we'll carry on with this after lunch and some food. Any questions? Excuse me, if I will eventually start to pull the cup round, okay? Proportional to engine speed, and along with the reduction gear, will give you the indication, yeah? So, does that make sense? Okay, good. Anything else?
No.
Okay. Right, folks, we'll move on. We'll take it nice and easy today. A bit more on EPR. Okay, there's a few bits to look at there. Pressure readings are normally just, there's no units as such, hence it's 1.6 to 1 or 1.07, just a unit. There's no specific units for the thrust itself. Okay, let's move on. So EPR, minimum takeoff rating. So we'll look at what's called minimum takeoff ratings. For a low bypass ratio engine, it is your turbine outlet pressure and your compressor inlet pressure. Standard EPR, okay, the outlet over the inlet. And there's a nice example of a low bypass engine, yeah? Nice little sort of twin spool low bypass engine there. A classic EPR. Smart. And for a high bypass ratio, well, we mix a bit. Remember, we've got the cold stream air and we've got the hot stream air. So from the hot stream from the core engine and the cold stream from the actual fan, which bypasses, and that mixes together. So now we've got two exit pressures comparing to the intake pressure. So we've got, as you see, you've got turbine outlet and fan outlet. So basically the hot stream and the cold stream integrating together, being mixed, comparing to the compressor inlet as well. So that we call integrated EPR. It's still EPR, it's still exhaust pressure over intake pressure, but we've got two, in effect, exhaust pressures, the cold stream exhaust pressure and the hot stream exhaust pressure. So mix them together, that makes one exhaust pressure, and we put it over intake as we did for standard EPR, but this time we've now got integrated EPR system. Okay, so pretty much the same thing, but more specific to a high bypass engine. So integrated engine pressure ratio. Sensors, we'll need some sensors to get all this information. So the inlet pressure is sensed by a single pitot type probe, which is situated just in front of the compressor. Now, a pitot probe consists of a static dynamic movement. Okay, so you've got the fluid, the flow moving into the Peter probe, which is calibrated, and then you have the inside the static pressure, the high pressure, and the low pressure mixing together, and then that will give a reading to the sensor. And you learn more of that in specific topics. Turbine exhaust pressure, okay, sensed by a number of probes. You're looking at usually around about 6 distributed evenly around and radial around the exhaust. You're looking at a P6, a P7, that sort of thing. Inlet pressure would also be P1. But they both feed into what's called the pressure transmitter. So the sensors sense the pressure, they send it to the transmitter, then the transmitter is going to do quite a few things, as we'll see shortly. Fan duct or fan outlet pressure, again, is sensed by one or more probes, depends on the engine type, into the outlet guide vanes or core engine support struts. Again, the pressure is fed from there into the manifold, which holds the exhaust pressure. And again, the pressure is read off by the pressure ratio transmitter as a mean or an average. Remember, mean, median, etc. A mean just means an average of both pressures. Hence, you get the integrated pressures. That's just an example of where they're coming from. So at the front of the engine here, you've got a P1 probe, and at the back, we've got a P8. Okay, it could be P6, P7. Okay, just depends on the engine. Again, you have sensors, various sensors all around about as required. So there's your IEPR transmitter, okay, inside of the engine. Again, just a basic setup. So the transmitter itself, intake pressure is present in 2 to 4 bellows. And I've looked at bellows or capsules like we saw before in the fuel system, which are radially disposed, so they put the round away at a central point in a frame. Of the other 2 bellow units, one holds what's called integrated exhaust pressure, the fan exhaust and core exhaust pressure, and the other is in an aneroid capsule, which again, we've seen these types before in the fuel system, and that's used as a reference point because we've got obviously sea level pressure within the aneroid evacuated capsule. The frame is held in a gimbal unit. Remember from physics module 2, the gimbal is the frame that holds the gyro in there. Well, this is a similar sort of setup. We've got a gimbal, which is on an axis, which in turn is held in a yoke, the main frame. So when a difference in pressure input is felt, the frame itself will try to move in the gimbal, which will in turn in the frame itself. So it's almost like a gyroscope in effect. And we need some sort of reference or sensing pressure back from that. So the gimbal has a good old friend, the LVDT, the linear variable differential transformer, mounted onto it with just a sensor giving positioning back. Where else did we see our LVDT? What system was that fitted to? If anybody remembers? Where else did we see an LVDT?
In fuel.
Yes, well, it does do with fuel-ish. What was the fuel doing? What was it sensing? An LVDT sensor was used for what? What did it need to know position of? The LVDT gave the position of a certain component back to the FADEC, and that was the position of the somewhere in the compressor. Remember? To do with the CVG. What was the CVG again?
Cross bleed valve.
Not a cross. Compressor variable geometry. So your VSVs, your variable IGVs was also, especially in VSVs, they would give a feedback through the LVDT sensor back to FADEC. So again, we're using another same component, but this time for the pressure ratio transmitter, which gives feedback to the system. In the gimbal, now the gimbal's at a balance, as it says there, your sensor, the LVDT sensor, will send an error signal, depending how much it's out of balance, to an amplifier. Amplifier amplifies that, and onto a servo motor. So motor will actually move something now, and we call this movement a null movement of the gimbal. So it'll just set it in position. LVDT returns back to the set position and will also drive a potentiometer. So we'll change the amount of voltage. Okay, you have a voltage output to indicate. So that change in voltage will give an indication on your actual indicator for the pressure ratio transmitter. So the transmitter is sending you the actual information. Nulling the LVDT will remove the error signal and to move the potentiometer a specific amount in the required direction. So again, indication on your gauge. Potentiometer will then send a signal through the indicator as such, and that's a typical example of a pressure ratio transmitter. So there's a bit more in depth of how that works. Just be aware of it. That's just, it won't go probably that deep in exam, but certainly be aware of how the basic principle of an LVDT, engine pressure ratio transmitter, and we're just getting feedback again from a sensor, good old friend, the LVDT. Okay. All right. And that's a basic schematic of what's going on. Again, it's just a basic electronic version of what's going on. There's your P1, obviously your capsules. There's your LVDT, your transformers, an amplifier, servo motor, and then obviously to the indicator. Okay, basic electronic, and that's the physical makeup of it. There's a potentiometer at the bottom, your little servo motor which will drive all this. There's your yoke, and there's the gimbal which all your transducers and sensors information sits in. Okay, and then obviously through amplifier to amplifier signal, and you'll have some sort of reduction gearings going on as well, proportionate to that. Okay, so that's just a little insight into what it looks like. If one fails, you're just going to replace it. Okay, you're not going to strip it down and check it. So the engine pressure ratio indicator itself is a classic example of what it looks like. There's the button which you'll put you can null or bug in position. Okay, so that's your servo indicator. So my animation is going out in mode there for some reason. Amplification of the signal is carried out in the transmitter. Okay, and the synchro system, like your RPM gauge synchro system, based on error signal we just mentioned, is used to pass the signal to the indicator. All right. Information display and limit indicator is obtained from the aircraft computer, for the ADC, and it will display in takeoff, climb, cruise, and go around mode. So make a note of those four, please. So your engine pressure ratio limit indicator will display in takeoff modes, climb modes, cruise modes, and go around modes. Okay. And there's sort of typical example, same one's in your book, if I remember right, yeah. So there's your engine pressure ratio indicator. Again, you've got 1, 1.2, 1.4. Again, no specific units, no actual pressure on there. Okay. There we go. Okay, other indicating system you might come across. Just pass that one. Again, oil pressure. This one case, a standard gauge here is a standard oil pressure gauge, from 0 to about 150 psi. It's sort of minimum pressure red, it's sort of maximum there. Remember, 124, we don't like 124 because it oxidizes. Green is good, we like to keep it in the sort of green range. 70, 75 psi is pretty much standard for a piston engine, thereabouts. Anything below that, again, remember your LP, especially for the APUs, the LP2 at 55, 45, and that sort of thing. But a jet engine is a similar sort of setup as well. So we need to know how much oil pressure we've got, because if we run an engine with low oil pressure, or indeed no oil, we need to find out what's going on there. Okay. Typical sort of setup for checking oil pressure. This explains a diaphragm spring type sensor. So in this case, we've got a spring sensor which is keeping the contacts away. Okay, we've got oil pressure in here. Now, as long as the oil pressure is sufficient, the spring will keep it away, but if oil pressure drops, the spring will push down to a contact and indicate low oil pressure. So providing this oil pressure is sufficient, high enough, it will keep this contact away from this bottom contact, just by pushing it up the way. Nice, simple. But as soon as you lose oil pressure, Well, the spring takes over, pushes that contact down onto this one, and that'll make a signal saying we don't have any oil pressure or low oil pressure. And then over to typical classic boarding tube. Again, boarding tube type, the oil pressure actually goes into the tube. The more pressure there is, the more it will expand. Again, providing it has enough there, it won't make the micro switch. But downside of that is you've got that going to a gauge. Well, you've actually got oil physically going into a gauge, which in olden days that was okay. But oil going to the back of a gauge, well, if that breaks or fails, then it's going to make a little mess, isn't it? So it's not ideal in the cockpit. So it's all nowadays all electronic further down the line. Okay, so that's a couple of examples of diaphragm ones and a spring stroke boarding type tube pressure setup. Variable capacitor pressure transducer schematics. Yeah, this is the more basic type ones you'll come across for temperatures. So a capacitance type thing. Got a reference point, a potentiometer, variable capacitor, an amplifier to amplify the signal, a velocity generator, a motor, and some sort of synchro as well. That'll direct a signal to a millivolt meter, digitizer, etc., and a light emitting diode. And again, we shall see how it goes from this. That's the basic setup. Oil temperature, again, just like oil pressure, we need to be in the green zone. We don't want to get too hot, but certainly that'll be in startup, and then green. Once we get to non-stand oil pressure, it will be fine. So a number of ways of measuring that. Again, it could be physical, direct thermocouple sort of setup. You could have a simple thermocouple in the stream. The usual method, though, is to use a coil of temperature-sensitive wire in a tube, so basically a thermocouple, and using a Wheatstone bridge for the outer balance. And that will cause a gauge to indicate the correct temperature. Fuel pressure, another one we need to know. Okay, fuel pressure, right off much the same as oil pressure. Again, the transmitter can take the same form as an oil pressure transmitter, and the gauge will look very similar, but again, also being fuel, calibrated at lower pressure readings. Okay. Most fuel pressure indicated by a light operated from a pressure switch rather than a pressure transmitter. You might have a fuel differential pressure transmitter right beside a fuel switch. So we just need to know when the fuel pressure is not there, but we can also have a fuel gauge that actually shows how much pressure we've got in there as well. Switch will be a capsule diaphragm, again, operating a set of contacts at a predetermined value. Low pressure switches are installed in the engine fuel system as a warning against possibility of cavitation of the aircraft fuel system, because if you've got no fuel flow from the aircraft and the engine's still spinning, that's just going to suck all the fuel out the pipes, and if there's no fuel left, then it'll just keep sucking the pipes and then they will just cavitate. So if we get an indication in the cockpit, especially going back to the fuel systems, we saw the differential pressure switch, which will have not a bypass for the filter, but it allows us to know if the fuel filter is about to come blocked. Remember, we saw that the other day. No point in letting us know when the fuel filter is blocked, because that's too late. So when it's about to come blocked, we'll get indication, and likewise, if we get a low fuel pressure indication as well. So again, you might have a differential pressure switch fitted across the filter as well. And that's just a side version of what we've got there. Pressure inlet, diaphragm, some sort of contact arms, so basically a mechanical micro switch used by fuel. Very important one, we've got a fuel flow metering systems. Again, what the purpose is to tell us how much fuel is being used at specific RPM settings. And there's various types of flow meters going about. We'll look at some of the basic ones. Okay, so again, measurement is, again, depending on the aircraft type. So monitoring fuel flow of an aircraft, engine provides indication of flight performance. And also, making calculations, can we actually fly to where we're going for? Maybe an aircraft has been off course slightly, it's into a headwind, so it's struggling to get to where it's going. Well, you can tell by the fuel flow and the quantity of fuel you've got left, is there sufficient fuel to actually get where you're going, or you're going to have to turn back. And likewise, if you've got a tailwind, you can calculate how much fuel you're not going to use. So it's all to do with cost as well. So types of flow meter. One of the first types is the velocity of flow. Now, this is the velocity at which fuel is moving. It is measured in meters per second, but it's very rarely used. Okay, very rarely used, that one. You've got volumetric flow rate as well. So as it sounds, volume. This is the volume of the fuel that is moving past a given point in a given time. It's all over time. All your fuel flows are all over time. This time it's measured in gallons or litres per second. Another one is a mass flow rate. Again, mass flow of the fuel flowing past a given point, again, in a given time. It's all over time. An SI measure of a mass flow is kilograms per second, but aircraft flow meters are sometimes calculated in pounds per minute. But normally it's kilograms per second, but you might find occasional one at pounds per minute. And that is the most common form of fuel flow measurement you'll find in your commercial aircraft. Indeed, when I worked in military aircraft, that was the most common, the mass flow rate. So if you've got a question saying which is the most common type of flow meter, it would be the mass flow rate type. Okay, so worth highlighting that one. Mass or volume consumed. This is the total quantity of fuel used. Again, measured in kilograms or pounds. All the meters might still be calibrated in gallons or litres possibly. Okay, so just be aware of that. But again, new ones tend to be kilograms or pounds. So let's look at one of the first ones. We've got a helical vane flow meter, normally used in high flow rates to measure. What you've got at the front, especially a tube with an impeller. So as the fuel goes through, it will spin the impeller. The straightening vanes here, just like IGVs on your compressor, they help guide the fuel flow onto the propeller and actually prevent it from giving false readings by straightening the fuel flow out. Okay. So high flow rates, multi-bladed, again, axle and rotation, very common one. You have electrical connector, supporting vanes at the back of it, just a simple impeller. The faster it's going, the faster, because the size of the tube and the type of impeller will all be calibrated for every one revolution, will indicate the specific amount of fuel flow going through. Okay. You'll have a small magnet in one of the vanes, which is just indicated here. You can just see where my laser is pointing there. Okay. Infect a coil to the buoy meter. Each time that magnet goes past, you'll produce an electromagnetic force field, okay, from the coil. The amplifier will count the pulses, compare them to a time base, and then pass that information onto the gauge. Okay, so very simple, straightforward one. Then we've got variable area flow meters. There's a couple of types of these ones. The principle of what's called the square drop law. In other words, mass flow equals the area of the orifice, or the size of the gap, multiplied by the square root of the pressure difference across that gap. So we end up with a little formula of mass equals area multiplied by the square root of the pressure drop. Okay. Therefore, the gauges will be calibrated in pounds or kilograms in this type. And in fact, achieved in two ways. You've got two types. You've got orifice and a plug flow meter. We've got the vane type flow meter. This is a very basic one. You've got temperature variations. Basically, the more that plug moves, then the bigger the gap here is. Okay, again, to a potentiometer to your gauge. So the more flow, the more pressure, the more it will move. This, you might call it a plug, to be honest, as it sounds, will move it off its base, which will increase the gap and increase the calibrated amount there. Now, diaphragm fitted in parallel with orifice to correct for changes in specific gravity of the fuel, because there are different types of fuel out there. Again, we used to do this manually on old aircraft. Nowadays, it's all done. The fuel flow meters tend to compensate this automatically now. So if you do put a different type of fuel with different SG in it, the fuel flow meters will read accordingly. They can compensate for that. Give an example or a parable to that is if you put on your, go back to my cars again. If you have your standard fuel in your car and you're reading 30 miles per hour or 30 kilometers an hour, that's fine. If you go and put a bigger wheel on, say you went from a 14-inch wheel up to about an 18-inch wheel, you've got a bigger wheel, well, you'll actually be going faster than what the indicator's reading, because it takes longer for that wheel to do one revolution. So in other words, your car's, well, although it might be doing 30 kilometres an hour, you're probably doing about 40 kilometres an hour, thereabouts. And likewise, if you reduce the size of that wheel, you'll be indicating you're going faster, but actually you're going slower. Okay, so with these type of things, these account for those changes in sizes and flows. The one we saw earlier on, which looks like a boat and a rudder. This is the vane type flow meter. Again, it's freely pivoted. So this rudder type system in the back here, the fuel comes in, it will push against this measuring vane, and as you can see, there's a tiny gap that does get slightly bigger as it goes round, and it's a calibrated gap. So the more that moves, the more it allows a little bit more fuel past it, back out to output, which pushes on a spring, which pushes on a potentiometer, and again gives you the correct amount of fuel flow. Again, very clever bit of kit. So that's your vane type flow meter. So again, a magnet and a potentiometer. Okay, so that's a basic one there. But the fancy one, a rotor torque flow meter. As it sounds, it's to do with torque, the twisting moment of the actual internals of the motor itself. So this flow ensures that the calibration variations caused by different types of fuel, change of fuel temperature, are kept to minimum. So this is the best one if you change your fuel and indeed the temperatures surrounding the fuel. Okay. Torque is proportional to fuel flow. So the more twist, that means it's proportional to the amount of fuel that's flowing through it. Okay. So you've got two pickup coils, just like a phonic wheel, but if we change the distance of the phonic wheel sensors, you get a bigger gap. And likewise here, with the fuel going through there, it's going to twist it as it's spinning around. Okay, so the greater the difference, or the speed of the two, the differential and the potentiometer there, which will give a far bigger reading on the signal for your indicator. Okay, so a transmitter and a single casing, and then obviously your pickups, one for the drum and one on the propeller, or the impeller, I should say. There's another insight into it. So you can just see one here, there's your sort of turbine itself, which gets spun round, the fluid shaft. We get a bit of lag. It almost works on the same principle we just saw with your RPM gauge, the drag cup. The torque will be spinning round, okay, and depending on the rotation of the actual body here, okay, the more that moves compared to the other one, the more the deflection, the greater the amplitude or frequency depending on the movement. All right, so that's your types of flow meters. You can just see there, number 10, there's your pickoff coils, okay, pickoff assemblies. So every time it spins round, you'll see where it is. You've also got a retaining spring as well, which, like the RPM gauge, the little spring there, which just resists the movement. So again, with a torque meter, it's the torque. The main thing to remember is the torque is proportional to fuel flow. Then we move on to vibration. Okay. Let's check on that one. I probably won't go over there. Vibration. Okay. So, especially on piston engines, lots of vibration, turboprops, a lot of vibration, and even standard jet engines, you're going to get vibration. Okay. Pure by the flow of the gas going through, that will cause problems. So during the manufacture of a gas turbine engine, you've got to make sure that special attention to specified tolerances, the balancing of the shafts, the fitment, the blades themselves and the fit to compressors and turbines, they are set in a specific location. Each blade will be weighed. Everything in an engine will vibrate. There'll be natural resonance where you can't get away from it. It will have a vibration amount. Everything we're in at the moment is vibrating. Some are vibrating very slowly, like the mountains, and some are very, very high. Like the voice coming from me, you're getting a high frequency coming out. Again, so we need to check certain vibrations on aircraft, we keep to a minimum. So just remember how you indicate usual sine wave here, you've got displacement. So remember, going back to your physics, you've got one wave all the way here. Okay, so start and the finish. Amplitude is how intensity it is. The frequency is how close that sine wave is together or far away. So high intensity frequency, very close. Low intensity frequency, very far away. The power in that is the amplitude. And if you go peak to peak displacement, that's max amplitude. Okay. Again, all measured in microns. Vibration sources, well, gas turbine vibration are generally classified as self-generated or externally excited. Self-generated, again, due to the unbalance of rotating parts that may be a result of uneven weight distribution during manufacture or assembly, or even damage. You know, we can get some of that, but normally when they're made, there's always going to be a bit of vibration. And when I used to work on a test bed, we'd put the engine in a stand, we'd run the engine up, and we'd do a vibration analysis. And we have to produce a graph, which I'll show you shortly, that allows us to pass the engine off with an acceptable amount of vibration. You never get rid of all vibration, there's always an acceptable amount. But again, damage, wear, contamination, distortion of a rotating assembly, just normal use, can cause vibration as well. Externally, caused by means other than the balance of the engine components. And that may be due to disruption of airflow through the engine. So if you go back to your CVG, your ACC and your RACC, so maintain the tip clearance for the compressors and the turbine blades. If that's too small or too large, we'll get buffeting of air going past air or slowing it down, and that can cause vibration purely from air. So you can make the blades vibrate, giving it an indication of vibration, which will be transmitted through the engine. The pickups to sourceless type of vibration are normally fitted to monitor the high and low speed rotating assemblies. Now you might have one, you might have two, you might have three, it depends how many you need on the actual engine itself. Okay, usually mounted radially on the engine casing, adjacent to the internal position of the appropriate turbine section. Okay, so as engine vibrates, the pickup body and the coil will move, and due to inertia, the magnet tends to stay its original place in space. The resulting movement of the sensing coil will therefore produce an EMF in the coil, and the magnitude of the EMF will depend on the vibrating force, and the frequency will depend on the rate of vibration. Okay, so you've got springs in there, magnet will stay there, so as it's vibrating, that will induce an EMF. Transducers, they're made of crystals, specific crystals. So this is a different version of a pickup. Working on the principle of piezoelectric, can be used. A suitable crystal, stretched or squashed the ions in the crystal and displaced to normal position. And the potential difference across that will cause a signal to be produced. So suitable crystals you've got are quartz, tourmaline, and the piezoelectric ceramics, which are lead, zirconate, titanium. Okay, so it's the three main types of crystals: quartz, tourmaline, and piezoelectric, or pizzas as I call them. Okay. And that's the most common ones you'll come across. When you're fitting these transducers, because they've got these quartz, tourmaline, and piezoelectric ceramics in them, it's very important that the screws that screw into the body, you get special torquing, a very small torquing, a very fine torque. If you over torque it or under torque it, then you could potentially induce too much pressure in the casing or not enough pressure in the casing, and that will give a false reading. We had an indication where one of the old engines we had on old aircraft, they got rid of the old system, they put this new transducer on, and every engine was failing. They couldn't understand it. It was too sensitive. It was picking up the minute amount of vibration. There was nothing wrong with the engine, but these transducers were too sensitive. So to go back to the old ones. Okay, but you tend to find this sort of type on more modern aircraft and engines now. All right. Inside there, excuse me, there's your crystals, and these crystals, the center get a positive charge and the center of a negative charge. So as they're bouncing about, they're vibrating, these crystals produce this stretching, a squashing, which will give a certain type of indication. And that'll have to go through an amplifier because the signal's too small to give to a gauge. So these ceramics, the quartz, etc., will give, due to the squashing of them, the vibration of them, they will give a little signal, and that'll go to an amplified, and give it an indication in the cockpit. And again, at a predetermined level, you might get a warning, a light might come on, or even an audible warning as well. Here's some photographs of the typical sort of transducer. They're not big at all. The ones we've got there, certainly on this side here, this side here, is very typical of the ones you might come across. Again, they are specific to specific sizes. They'll come with their own adapter plate. The adapter plate will fit to the casing and such like. So again, check your part number, make sure you handle them with care. If you drop them, it's probably broken. You won't be able to tell externally, but certainly internally, that might have been damaged because of crystals inside. Very, very sensitive bits of equipment. As you can see, we've got bayonet type connections that fit onto the plugs. Make sure they're clean. Again, that can produce some false indications. An indicator, it's possible to discriminate between the rate of vibration, the frequency, and also the amount of vibration, which we class as the amplitude. Okay, going back to the standard sort of setup, there's a vibration limits. Okay, we're getting a 2.2 thereabouts. They will be specific to engine on its own, and once the engine's fitted to the aircraft, there'll be a different limit that's worked out because there'll be standard vibration in the aircraft, which can be transmitted through the couplings, the fasteners of the actual mounts for the engines. So there'll be a limit for the engine, let's call it 1.5, and maybe a limit for the aircraft, again, maybe 1.5. So total is maybe a limit vibration of 3. Okay, so again, 2.2 here, that's maybe within limits. Again, that's just a general example. Now, by checking the difference between the frequency, the rate, and the altitude, most vibration test sets will be possible to switch between the two, so the amplitude can be studied and the various frequencies as well. Now, by doing that, by checking between the frequency and amplitude, we call this doing a frequency sweep. Okay, you want to highlight in your books. Call that frequency sweep. Additional pickups, transducers, readings can be taken, so we can add more transducers on at different positions of the aircraft. What I mean by is tangentially, axially, and radially. Okay, I'll show you a diagram in a minute as well. Examples of frequencies you might come across. This is a typical graph you might find. Every rotating component will have a frequency where it vibrates. That's just natural. So we can actually figure some parts out. So, an example. Let's say we were running an engine and we got a vibration caption came on, and we've got NH here, or N2 is 90%. Okay, so let's look along at 90%. So we've got speed on the bottom here, NH spool. So we read along the graph 90% and put a line up. Okay, we get the frequency, because remember frequency is classed in hertz. So we got the frequency side of the graph, and we find 140, and we draw a line across there as well. And we've now got an intersection at this point here. Now we found that at 90% NH, we got a vibration warning, and it was 140 hertz. It happens to be on the centrifugal breather. So the good chance is the bearing within the centrifugal breather is on its way out. Okay, so we would go and change the centrifugal breather. Sometimes we do find random ones over here, or down here, or in between the lines, or not quite on the line. Again, it comes down to experience. We get harmonics of vibration. So actually, let's say we got one at 280 up here. We've got a frequency up here, 280 and 90. Well, it's not touching anything. Well, 280 would be the second harmonic of 140, wouldn't it? So it's a slightly different. So it might be the bearing, or it could be the bearing itself rotating within the housing, given a harmonic. So by deduction, we can come down by looking at harmonics. And the first harmonic, the fundamental frequency, in this case, would be centrifugal breather. All right. So sometimes it can just be in the line, it can be very close to it. It gives you a good indication where it is. Things to watch out for when you use a test set to check vibration. The leads are very sensitive to background vibration. So when you've got a test set on the ground, you've got the power lead and the leads connected to your connectors on the engine, make sure those leads in the test box don't cross over a power lead, because they will pick up the frequency of the power that's flowing through the power leads. Likewise, background things like lights. Lights affect 50 hertz. Your power sets will induce vibration as well. So again, they've all got natural vibration in them. So there we go. That's a little example of we found that potentially the centrifugal breather is on its way out. It's causing a bit of vibration. And you'll probably find that if it matches the vibration, as you increase the RPM, that would probably go up in line with the breather. If it goes away, it could be a spurious one. But again, you will do specialist courses on vibration analysis. It's a good one to get to become a specialist. You get authorised to do that. It makes you more valuable to the company. If you become more valuable, you get more money. That's a good thing. Okay, so a typical graph there. Then we've got what's called a vibration trace. This can be done in real time on the vibration equipment. You can actually see the spikes moving along as you're doing an engine run. We can also print them out. Now in this case, we've got a pass-off test, which means this is a sort of graph once we run an engine, we do a full vibration run, and then we print the graph off and see what we've got. The green line here represents a standard, yeah, that's okay. I mean, it might be higher, it might be lower, it depends on the frequency. Amplitude we've got here is 10.5, and as you can see, we have got a spike at 10.5 microns. Okay, and this is the engine at 90%. We found that HP fuel pump pass-off test bed figure was at 2.5. Well, this obviously exceeds 2.5. These other spikes are just background stuff, but we've certainly got a frequency of 250 Hertz, which we found to be HP pump. Well, HP pump's well out, isn't it? So we're good off to go and change the HP fuel pump and do another vibration trace. Pickup positions, as I said, radially, axially, and tangentially. So tangentially is perpendicular to the axis, radial for round, and axial in line with the axis. So there's the typical sort of positions you would find fitted to an engine. Here's a typical circuit. Okay, get your engine, the pickups, and you might have 115 volts, 400 hertz supply, single supply. So not 20 volts this time, but 115 volts. You have an input and a test, so you can press the test, the lights are all working up. You have an engine VIB indicator where at a predetermined level, that light will come on. You will see these lights lighting up every so often, going up and down, depending on more thrust, more power you're putting into the engine, the lights will go up and down, and eventually reach a predetermined value where it'll ding, 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 the light will come on, bit of a warning, you've had a vibration. Yeah, amplifying filters. Okay, we need filters to take out residual stuff that shouldn't be there. You don't need to know all the different frequencies. Rectifier to sort it out because 150 volts going in, we might need to rectify that voltage. And the warning circuit light itself, when a predetermined value, it will come on and stay on and indicate to the pilot and indeed to the engineers. Okay, anything else I want to pass you on that one? I think happy with that. Okay. Good. Okay, any questions on some of that stuff? Let's see where we are now. Torque. Okay, so just maybe quickly recap that one and make sure we're all happy with that before we move on to torque. There's quite a lot to go through. Okay, so just step back a word. What was a frequency sweep again? What was the term frequency sweep? What was that about? I remember what a frequency sweep was. Anybody?
Yes.
Jack and Gendera?
Yeah, hello.
Yeah, what was a frequency sweep?
It's a indicator for the vibration test.
Yeah, what are we comparing? Or what are we looking at individually?
We are looking for the amplitude.
Yeah, we're checking amplitude, yeah. And what else?
Switch between the two so that Amplitude can be situated to various frequency.
Yeah, so we're comparing the difference. The rate of frequency and the amount of amplitude. So
And the amount of rate of vibration and the amount of vibration.
Yeah, that's right. So we can actually isolate either or. So we can have a set frequency. The frequency might not change, but certainly the amplitude could change. Okay, and likewise, the amplitude stays still, but frequency could increase depending on the RPM. So we can actually use these vibration traces, those example graphs I showed you, how to isolate between the two. If we go back to that diagram there, as I said before, you might get harmonics. Again, once you do a specialist course, you'll learn about this if you do a vibration course. Where we've got 250 hertz here, let's call this position here 500 hertz. Or in fact, no, let's call it 750 hertz. So we've got a spike at 250, and we've got a spike at 750 hertz. Well, we've got 250, 500, 750. Well, that's a second harmonic of a fundamental frequency. So this, I used to call them ghosts, right? This would be a ghost of the original frequency. So although you might find the frequency here, you think, okay, we can figure it out. If you went back to this graph, you'd be figure out it's still the HP pump. Okay, not saying this one is on this graph, but that's the sort of examples you would learn through experience and time. These sort of passive graphs, normally you get a couple of spikes here. This pass-off rate would be maybe a line about here would be standard. Any vibration below that would be acceptable. Now, saying that, sometimes when we used to test engines, we'd maybe get an engine that maybe have a spike that was very, very close to the pass-off. Now, if it's that close, it's just going to get worse. So we would go and check it, find out what the fault was, and then if it's possible, we go and change it and then do another run to get the spike a lot lower. So spikes like these, that's pretty much standard, yeah? That's sort of standard what you might get. Then we've got, you can certainly see here, harmonics of this fuel pump. Okay, but they should all be under a certain line, which is fine, yeah? Okay, so yeah, frequency, that was checking between the discriminating between the amount of frequency, the rate of frequency, and the amount of vibration, or the amplitude. What was the names of the types of crystals we use in the transducers?
Quartz.
Yeah.
Tourmaline.
Yeah.
And piezoelectric ceramics.
Yeah, good old pizzas. I call them pizzas. Piezoelectric ceramics. Good. So yeah, when crystal is stretched or squashed, it's squashed the ions in the structure, yeah, and the crystal displaced from their null position, and that change of position controls or sets off a signal. The standard pickup, what sort of energy does it convert? What does it convert? What energy does it convert? Yeah, simple as that. Basically like a guitar string. You vibrate a guitar string, get vibration. That's mechanical. Let me hear sound. Well, this time it's mechanical between the magnet and the coil, makes an EMF, and the greater that intensity, the greater the electrical signal. Okay, good. What was the difference between a self-generated vibration and externally excited vibration? What's the difference between the two?
Yeah, self-generated is from unbalance of rotating part.
Yeah.
And external means unbalance of engine component.
Yeah, it could be due to airflow, the gap between the turbines, compressor blades, and that sort of thing, anything exhaust, malfunctions with airflow control, not working correctly, like VIGVs, VSVs. Okay, so yeah, good. Self-generated, yeah, it could be damage, fog damage, and that sort of stuff, yeah. Okay, what's the other one I was going to give you there? How do we, what is frequency expressed in? What is frequency expressed in? What's the units?
Hertz.
Hertz, yeah. Cycles per second. Okay, so 1 cycle per second or hertz. Yeah, good. All right, let's see. I'll leave that one. Give me an example of a type of flow meter.
One second.
Yeah, sure.
Odometer?
Which one, sorry?
No, what was the question?
Give me an example of a type of fuel flow meter.
Helical vane flow meter and variable area flow meter.
Yeah, good, yeah. The vane one, yeah, it's good. Helical one. And which type of flow rate is the most commonly used? There's 4 types of flow.
Mass.
Yeah, mass flow rate. Just think the biggest one, mass. Think massive, yeah. We've got the velocity of flow, we've got the volumetric one, we've got the mass flow rate one. Again, there's a table in your book. It might still be the same as your old books. Just highlight the mass flow one, most common rate. And what's it expressed in? What are the units for the mass flow rate? What are the units?
Per second.
Yeah. Or
pound per minute.
Pound per minute.
Pounds per minute. Yeah, good. Good. Okay. Which type of flow meter would be used for where high flow rates are to be measured? So which type of flow meter would be used where high flow rates?
Helical vane flow meter.
Yeah. Just think of impeller on a boat. That's high flow rate. Okay, good. In that same type of component, what helps prevent false readings?
Straightening vane.
Yeah, the straightening vanes. Yeah, just think of straightening vanes like IGVs, same sort of thing. Instead of air, we've got fuel. Straightens the fuel out a bit before it hits the. So it prevents the swirling action before it hits the impeller. So we want the fuel to be almost straight, then hit the impeller. If it's already spinning with the impeller, it won't give the same effect. So we use the straightening vanes to help prevent that. Good. Now, in my PowerPoint, I didn't mention it, but have you ever heard the term delta P? Does anyone know what delta P means? It's an American terminology. You might see a little triangle on even an oscilloscope. That means delta. Now,
pressure difference.
Yeah, pressure difference, yeah. So differential pressure. Something's annotated as delta P. Americans brought this into line. So a little triangle beside P, T, or whatever, that means the pressure differential or temperature differential. Anything with delta means changing. Okay. And with the fuel pressure one, if you've got a pressure differential switch, if it's about to come blocked, the warning that the filter is about to come blocked. Okay. How do we measure oil temperature? What's a standard sort of setup? How do you measure oil temperature? What's a simple method?
Thermocouple.
Thermocouple, yeah. Or, yeah, pretty much the same thing. A thermocouple is a sensitive wire in a tube. Again, the tube is placed into the stream. So basically, yeah, a thermocouple, because you go back to the exhaust thermocouples, you've got your hot, your cold junction inside the tube. Well, to be effectively the same, this is just a basic thermocouple. Good. Okay. All right. Other monitoring systems, yeah. Again, the oil side of things, a lot of stuff you will see now indicates on a VDU, visual display unit, again, or the computer. Okay. Well, I'll just go back slightly to a diagram meant to show you. Reference to piston engines. Excuse me till I go back a bit. Will I do this? I'll find it. There we go. Right, I meant to say on the oil pressure switch, We mentioned this in some of the piston engines, definitely. You've got a yellow arc range, which is cautionary. Anything in the green range is good, but certainly when it comes to piston engines, remember, piston engines are intermittent, so there's a point of vibration in the engine. It doesn't like to be at a certain RPM. It will vibrate quite a lot. And you'll find that arranged with the oil pressure. A piston engine does like to get a certain RPM. You tend to find this red area as an RPM range where it doesn't like it at all, especially for oil pressure as well. And then as you exceed power, you have another range as well, takeoff and cautionary. So if your max pressure limits, your low pressure limits, and an area where you don't want to be sitting in because of the vibration, especially in piston engines. But likewise there, a typical green area, when your engine's working normally, it should pretty much stay in there. It might overswing a little bit or underswing occasionally. It should come back to within that range. Around it, usually 70 psi is pretty much standard. Okay. Again, they just don't worry about too much about the figures for there. That's just an idea. Okay. If I'm going back to an engine pressure ratio limit indicator, it will display 4 modes. What are the 4 modes for an engine pressure ratio limit indicator?
Takeoff, climb, cruise, go around.
Yeah, thank you, Personally. Yeah, take off, climb, cruise, and go around modes. Good. Okay. What is IEPR?
Is integrated engine pressure ratio.
Yeah. So what is the extra bit that is in there that's not in EPR? We've got EPR and IEPR. So what's the extra bit that's been added into EPR? It wasn't in standard EPR.
Mix the compressor inlet.
Not a compressor inlet.
Pressure.
Outlet. Yeah. So compressor outlet's the cold stream, and then your core engine, which would be your standard engine, would be your hot stream, exhaust pressure. So the fan pressure, your cold stream, and your hot stream, mix that together, and then compare that again to your compressor inlet. Good. Okay. What is the term we give to, I'll just mark it down before I forget, the term we give to the back pressure, we've given pressure across the nozzles and a reading at exhaust. So when we get the engine choke position, we get pressure thrust, and at pressure thrust is exhaust. What's the abbreviation we call that?
Bug.
No. What's the abbreviation? So, yeah, PEX.
Full form of PX.
Yeah, PX. Right. On the DPI gauge, DPI indicator, this last one before we go for a break, it's marked in inches of mercury. Okay. Somebody's got feedback. The gauge must be set by doing what? To insert an index number. Nice and easy. What do you do to the gauge? So how do we set the gauge? By indexing the number. Once you've found out the number. What do we turn? Nice and easy.
No, we didn't understand the question.
If we got the direct pressure indicator, we've looked at the graph, we found the index number, we then have to set the gauge. So how do we set the gauge?
Knob.
Yeah, so just turn the knob. That's it. That's all we do. What might you have to take in consideration?
Sorry, sir.
What might you have to take in consideration when you're finding an index number? Adjust it. Is it have the switch on or off? Osmani, I think there's no feedback there.
Yeah. जी तपाईँको माइक धेरै डिस्टर्ब आयो यार. Yes. Thank you.
Yeah, if you're setting your index on your DPI gauge, you might have to adjust for if you've got a certain thing switched on or off. What might affect the thrust indication switched on or off?
Anti-icing.
Yeah, anti-icing, yeah, because that's going to affect your thrust. Okay, good. Again, in the direct pressure indicator, it's only effective up to a certain forward speed of generally around how much knots?
50 knots.
50 knots, yeah. And what do they not compensate for?
RAM effect.
RAM effect, good. Okay, right, that's a good point to finish there for the moment. Let's go for a break and come back again in about 20 minutes. I'll just put this back to where it should be, and then we'll continue a bit more. Okay. Right, we'll just do a little bit extra. We'll do torque measuring. We'll probably sort of leave it there and do some recap from what we've done all today. We'll start with ground ring tomorrow. So we'll do a bit of torque measuring bits and pieces. Again, we've done some of this already with module 17. So again, because we're going back away, we've started module 17 first, and now we do module 15. This is what you would have covered first before we did 17. So hopefully that'll make a bit of sense as well. Okay, so engine torque. So we're looking at thrust, and we're also looking at torque. So thing to work again there. Right. So torque, again, alongside the RPM gauge, especially for a turboprop type turbo shaft, you have to look at the work done and the rate done independently. Now, the power developed in a propeller engine is also relative to the RPM. In other words, the faster the engine goes, the more power is absorbed by the propeller, and therefore the more useful it is gained. But now, when it comes to using it on piston aircraft, we've got to deal with what's called manifold pressure. If we have too high a manifold pressure in a piston aircraft, that can blow up the engine. Like it's not enough, we won't have enough power, so we need to work with the torque. Again, torque is also representative of the angle of attack of the propeller blades, especially turboprops and piston engines and that sort of thing as well. So there's a lot of things going on, trying to balance out what's going on with torque and thrust and everything else. So look at the turboprop and turboshaft engine. Again, we'll have the gearbox transmission on there. It'll be inside there somewhere. The propeller shaft, the main rotor shaft, again, all providing torque. And we'll look at the type of torque meters, as well as a few other bits and bobs. So the main types, strange enough, it was already, what's the two main types of looking at torque? What do you think it's going to be? Two main type of systems. Hope you remember from module 17. I know it seems like ages ago. So what do you think? So two main torque systems. Again, this was module 17, so I should remember this. Again, maybe not. Nice and basic. So what type of torque systems would we have? Just basic ones. The basic methods, if that helps. Anybody? Okay. I know it's getting late. First one, hydromechanical. So the other one must be. What would the other one be? We've got hydromechanical, and the other type of system must be.
Electro?
Yeah, electrical, simple as that. Mechanical and electrical. Hydromechanical, we use hydraulic pressure. And electrical, we also use the types of phonic wheel type setup, which we've seen already. So hydromechanical one, again, construction system depends on engine type. Again, most cases though, it will be operation based on the same principle. The tendency of some part of reduction gear to rotate is resisted by the pistons working drop cylinders secured to the casing. So what you've got in your book, I'm going to try to call this in a little bit here. You've got your sun gear. yeah, which is your crankshaft. Now the crankshaft is rotating in this diagram, looking at it there clockwise. So as that's rotating clockwise, that's going to spin the planet gears the opposite direction. And these are all going to spin within your ring gear. Now, ring gear is pretty much stationary. If the force is even there, then that's fine. But as they're spinning round, the more that spins, the more that these planet gears are going to try and turn this outer ring. And if the outer ring turns like that, it's going to move the pistons. Yeah, one piston up that way and one piston down that way. Well, if it increases up the way, that's going to squash the fluid in there, in effect, okay, which will increase the torque reading. So as that's rotating that way, it's going to rotate the other gear the opposite way. So the gear's going that way, so that gear's trying to push this ring that way around, okay, clockwise. It's trying to push it the same direction as the crankshaft, that makes sense. Okay, so this is moving round clockwise. The planet gears are going anti-clockwise, but as they're moving anti-clockwise, they're trying to move this ring gear clockwise, the same direction as the crankshaft. So the more that tries to move the ring gear, the more that will move these pistons up the way, which will squeeze the pressure in there, which will squeeze the pressure, and that'll be indicated on your indicator gauge. So that's a basic mechanical type 1. All right. There's a side-on view of what's going on as well with using the gears. So that's a basic hydro-mechanical one. All right. So depending on the speed of the engine, the resistance from the propeller to the gears, depends how much these pistons move, will depend how much pressure they put in the system and your final reading on your gauge. So that's one sort of type. That's using the piston method. Okay. Another version you can see here, you've got the shaft where the propeller sits on. Again, you've got the ring gear or the annulus. Okay, and there's your reduction gears at the back. You will have oil pressure coming in. You'll have your torque meter pistons. All right. Now, again, supply from cylinders with a torque meter pump. So there'll be a pump in the system that supplies the oil pressure and absorbs the loads due to piston movement, the oil, and then therefore subjected pressures which are proportional to the applied loads or torque and transmitted to the torque pressure indicating system. So on this side, this is what I took a look at. Let's look at the diagram. So what you've got is there's a pump supplying the oil in, which go back to the previous diagram, would be here. Okay. So oil, again, you're onto a piston. You've got a small bleed there because you need to be able to move that piston back and forward. This shaft here with the gear would be to the propeller, and this shaft here would be from your crank or the reduction gearbox anyway. So at no revs or very low revs or low torque, it's sitting at low pressure. Yeah, and we've got a slight bleed going off. Now, the faster the engine goes, the propeller's trying to move off. Okay, so you see my super animation. Okay, no expense spared, Steven Spielberg animation. You can see as the pump increases, okay, as the pump speed increases due to the speed of the engine, it provides more oil. More oil will then push the piston back the way, which will increase the pressure in here. Okay, so pressure will increase, and that will be indicated on your gauge. So gears rotate, they move a piston inside the cylinder. As shown in the image, power increases, oil pressure created within the cylinder increases, and that pressure transmitted to the gauge. The bleed hole within each cylinder allows the piston to reach a sensitive position as the torque reaches a point where it balances the thrust produced by rotation of the shaft. Okay, so again, that'll be linked to the other system. Any over torquing will obviously you have to watch, especially in piston engines, for manifold pressure, but any over torquing will be controlled as well by governor or maybe a propeller control unit. So it'll be all working together. If you're getting too much torque, then it's either up to the pilot or automatically by the system. So again, no torque or very low, so we've got low oil pressure here. Yes, the pump's spinning, but it's not doing enough to push the piston forward or rearwards in this case. So your indication here is quite low. Increase the flow, more pressure. Okay, no flow, no pressure. more flow, more pressure. So more flow, more pressure, and a tapping off of there gives you more pressure into your gauge. So the piston has moved back. So high torque. Again, you have to be very careful, especially in a feed turbine type 1, where you can actually over torque the engine because the feed turbine can rotate quicker. So that's your mechanical one. Electrical one is pretty much what we saw already between your wheels on the speed. So we're using two sensors. Torque is a twisting moment, isn't it? So we twist something, we're twisting, we're torquing it. So we're having two sensors, A and B, on two intermediate shafts. The more the twisting, okay, or the difference between those two sensors, the greater the torque, and that's produced electronically. So the principle of this one is it measures the deflection, so the gap between sensor 1 and the gap between 2, so indicated by this angle here. So the greater the angle, the greater the torque. All right. So basically, you have two phonic wheels set up slightly out of phase. They're not in line with each other, obviously. As probe 1 receives a signal, okay, this one here, from the wheel A, it will switch on the circuit on, and as probe 2 gets a signal, it will switch the circuit off. So obviously, the greater the distance, the greater the time delay between on and off. So the greater the time delay, the greater the difference in time will increase the signal, which will be indicated on your indicator. So in other words, the longer it stays on. Basically, there's your sensors you pick up on your tubes. You'll have, as it's sat in there, the torque meter assembly. Okay, so there's your propeller. There's your gearbox. There's the torque tube. So you've got outer torque tube and an inner one. Okay, so as one's free to rotate, outer torque tube. So the greater the difference between the two, the greater it stays on longer, which means the greater the torque. Okay, and that's the change. You see them out of phase. So that tube there represented by the colour red, and the blue one here. So they're not in phase. They're not in line with each other. That can be seen from here as well. Okay, a preset point. Okay, that's your basic electronic one. All right. Good. Again, there's a diagram in your book showing the gauge. I don't have it on this one, unfortunately, but pretty much there. So torque indication, there's the sort of thing you might come across. Okay. Gives you an idea of the gauges of what you might come across. Classed in percentage. Okay, classed in percentage. And that's an example from a Bell helicopter torque gauge. Again, it could be any sort of one. And what you would have there is R for rotor, which would be your main rotor, and T for tail. So you're getting two torque settings of the same gauge, but indicating two different components, especially in the helicopter. All right, and the same sort of thing here. You've got your N1 speeds, the N2 speeds, and there's your torque gauge there, represented by a percentage. Okay, so again, you're looking at a lot of things. It's all nice having all that stuff there. There's your warning panels. Again, anything's working, should have lights off. Anything's got a fault, the light will come on. All right, so you've got fuel flow, oil pressure, oil T, fuel left, fuel right, fuel pressure, time local, time Zulu, cabin pressure, outside air temperature. So lots of things to watch. Anything else to select. Again, it's all dependent on the aircraft. USB to download bits and pieces. Nice and compact, because nowadays individual gauges took up a lot of space. Now it's all digital, or LCD takes a lot less space. But you have to know and understand what you're looking at. That's the main thing. So that's a typical turboprop indicator there. And the last bit we'll do before we sort of recap is some engine warnings. Yeah, you'll see lots and lots of things that say when you start an engine up, you will have lots of warnings, all lights will be on, and as you progressively go through the startup phase, lights will start to go off. Okay, if any lights remain on, they're either meant to be on or something's not right. So as I say, you have alerts for, like we've got here, overspeed, hydraulics, generators. Again, you'll see as you get used to doing ground runs, which we'll cover probably tomorrow, you'll see difference of how to do ground runs. EPR indications, N1, exhaust gas temperature, N2, fuel flow, extra signal data, and there you go, there you go, N1 or NL, ITT, N2 percentages, fuel flow, kilograms, oil pressure, oil temperature, VIP captions, low pressure spool, high pressure spool, again, you'll see it moving up as a scale. Cabin altitude, delta, there you go, there's a little triangle. And then you can make it on the screen very well there. So cabin pressure, so change in pressure. Cabin rate, APU, off or on. And things like roll and pitch. Landing gear, 3 greens is good, 3 reds means the indicators are up. Flat position, spoilers, and so on, and so on, and so on, and so on, and so on. Lots of things, okay? So lots of things to work and look at. And again, the bigger the cockpit, the more lights you have to look at. But when you're doing engine runs, you guys will be trained on certain parts of the cockpit only. You won't have to worry about every single system unless it's also mechanical. If it's avionics or B2, leave it to the B2s. If you want to become B2, then you'll learn more as well. Okay, so there are conversion courses, you can cover that. So every cockpit's different, but in principle, you need to see the same things. You need to see thrust, torque, pressure, but it's fuel pressure, oil pressure, temperatures, vibration, positions of things. So there's lots and lots to look at. Okay, so that's just a basic insight thereabouts. So what I'm going to do now is I won't go any further today with the theory. What we'll do is do a nice little bit of recap again, okay, and take it up to about 4 o'clock and finish with it. So about an hour of recap, a little break in between, and take us. That's quite a lot of information to take in today. So tomorrow we'll start off with ground running, and which is a bit more fun. There's a few bits in there I need to remember, and go through some good old bits and bobs. Now checking on pages what we've got there, 143, 150, and we've covered 50 of pages today, so that leaves us perfect for tomorrow and Thursday. So I reckon by Thursday lunchtime we will have finished, at the latest Thursday lunchtime, we'll finish all book 4. So what we'll do on Thursday afternoon is we'll recap all book 4 as much as we can, and then if there's time left, we'll start recapping books 1 and 2, and then on Friday, as I said, we'll recap absolutely everything. So Friday will be purely recap revision questions. Okay, so your heads will be like that. Either you know all, or we've forgotten everything. One of the two. All right, so let's go back. Let's start as we usually do. Just go back the way. Again, on these panels as well, we call them the ICAS systems. Your engine indicating crew alert systems. It's all fancy now, all the analog gauges. There's days when I used to work in aircraft, you actually go and tap the gauge, and the gauge would start to move. All fuel gauges were all very old. You would have to tap the gauge and make sure you're getting the right reading. You don't have that joy anymore. It's all electronic, most of them anyway. Okay. Right. So let's go back the way. Let's go back to torque settings, torque tubes. So the more twist on the drag the torque tube, or the distance between the infill, would that make the signal longer and stay on longer, or will make it stay off longer? So as the two sensors move, will that keep the signal on longer or switch it off quicker? Does that make sense? So you've got your two tubes, the inner one and the outer one. As they rotate, and the more torque means the bigger the distance, the bigger the angle. So is that making the signal stay on longer or staying off longer?
Making longer.
Yeah, it's going to take, it's a bigger distance, so it's taking longer for it to switch off to the next pulse sensor, isn't it? Yeah, so that'll be indicated in your gauge. Okay. All right. So the two basic types of torque measuring were what again?
Electrical and
hydromechanical, yeah. So what's the basic principle of hydromechanical torque one? there's sort of two versions, but what's the basic principle between a typical sort of turboprop one? How does it generally work?
They in hydromechanical, the basic thing is they work on from the oil from the engine.
Yeah, but it might have a tapping of engine oil, or it might have its own tank possibly, depending if it's on the reduction gearbox. It can on small engines take a tapping from engine oil, or have its again separate oil. Again, it'll have a separate pump. It'll have its own pump. So as obviously the pump provides flow, and as we get the more flow we get, the more pressure. So as my daughter used to laugh because I try to teach her hydraulics, she says no flow, no pressure. So if there's no flow, there's no pressure, there's no indication on the indicator. The greater the RPM of the engine, it means the pump's going faster, which means there's more flow. If there's more flow, then there'll be more pressure in the system. So the pressure will move the piston, and there'll be a sensing line off that system to your gauge. So that'll provide an indication of torque. Again, must be carefully monitored by the pilot and indeed the system. Again, if there's too much torque there, that can overstress the engine, especially when you've got twin controls going on. If it's a single control, then you can usually work that okay. And likes of manifold pressure for a piston engine, so very carefully consider. Other version, the basic one, is to get a pump, and you've got the sun gear, the planet gears, and the annulus. So again, as the sun gear, your crankshaft spinning, or the reduction gear is spinning, sorry, the planet gear will spin the wrong way compared to the crankshaft, which will then turn to try the annulus, which is attached to two pistons. And the greater it moves the pistons, the greater it squashes the oil, which increases or decreases the gauge appropriately. Okay. Right, going back. Okay, if we go back to vibration transducers, and some of these transducers have a filter in them. A filter, okay? So from a pickup, say if a pick is amplified and checked by what's called a filter circuit. What does the filter circuit remove? What are we not interested in with vibration? Because everything vibrates, but we don't need to know every sort of vibration, but we want to get rid of some stuff. So the filter circuit filters out what? I can hear some on my monitor because I've got the microphone up quite high. So I'm getting a little hiss. What do we call that? That background noise. Just background noise, isn't it? So the filter circuit gets rid of any, we don't need to bother about like background noise. It's not really relevant to the engine. So any interference from other stuff that's not really relevant, it just filters it out. Some of you might have the fancy headphones, noise reduction headphones. Okay, you might have those fancy ones. So you can hear your music nice and clear, but it gets rid of background noise like cars going past or anything that's not really relevant to what's inside the headphones. And the circuit within the transducer gets rid of any sort of unwanted noise. Is it just nuisance noise, as we call it? Okay. Again, you can test the vibration circuit, and all is good. So again, going back the way, transducer works on a principle of what type of electricity?
So again, hertz.
Yeah. What type of electricity do we call it? Sounds like Domino's or Pizza Hut. Well, to say that. A transducer works on the principle of piezo electricity.
Piezoelectric.
Yeah. I keep thinking pizzas. I must be getting hungry. Piezoelectric. Yeah, so we've got the suitable crystals that used in the transducers, which were what again? What were the type of crystals? What was the names of the crystals we used in the transducers? Quartz, yeah, that's one of them. Tourmaline, good.
And again, pizza.
Yeah, such as lead, zirconic, good. Yeah, what is the rate of vibration measured in?
Hertz or CPS, cycle per second.
Yeah, frequency, good, yeah. So what is the amount of vibration measured in? No, that's the rate. Amplitude, yeah. The amount is amplitude, the rate is frequency, yeah. And what do we call that term where we can distinguish between amplitude and frequency? What do we call that method?
Is frequency sweep?
Yeah, frequency sweep. Good, frequency sweep. Good. And you'll find as well, if you ever come to do vibration runs, we used to have an overlay on the test kit, and the diagram I had with the standard vibration amounts for fuel pumps, oil pumps, whatever, we'd actually draw a graph on the screen, or maybe a bit of clear Fabon or whatever it was, and we actually draw the standard overlay. So we could actually, when we're doing a live vibration run, when you're doing a live vibration run, you see the vibration in real time. So any spikes that come up, we would see it come up against a certain point, and we can say, yeah, that's okay, that's the HP pump, just to experience. Again, just a little trick of the trade. But again, if you ever get a shot of doing it, it's very good. Okay, what do the pickups convert? What do your standard there's another one. Pickups are sometimes called accelerometers. Okay, transducer is sometimes called, another name for a pickup or transducer is sometimes also called an accelerometer. Okay, just a bit of terminology there. So what do these pickups stroke accelerometers convert?
Convert mechanical energy into electrical energy.
Yeah, good. If we found where the vibration was out of limits and it was due to a damaged compressor, what type of vibration are we classing that as? Remember the two types of vibration.
Once again, what was that?
Yeah, if we found we're doing a vibration run and we found that LP compressor was out of limits. We've got a high spike on it, yeah. And we did a check on it and we found some damage to the LP compressor. So what type of vibration? Remember, there's two names that were given to types of vibrations.
That is self-generated vibration.
Yeah, good. Self-generated vibration.
Because it's rotating part.
Yeah. Other one being due to external excited vibration, like we mentioned about airflow across the tips of the blades, CVGs maybe not working correctly, or VSVs maybe stuck. We're disrupting airflow. Yeah. So good. Good. Okay, that one's fine. Okay. Right, with relevance to a rotor torque flow meter, I've highlighted a few more bits which I'll try and put in the PowerPoint, but just to give you a heads up as well. The synchronous motor in a rotor torque flow meter, similar sort of idea to your RPM gauge. It drives the measurement assembly through a magnetic coupling, so again, very similar. Attached to the drum, and it's at a constant speed of 100 RPM. So if you see that in your old book, highlight that one as well. And also is impeller proportional to the fuel mass flow rate as well. Right, with a vane type flow meter, the chamber in the vane type flow meter, when the vane looks like a rudder on a boat, is it proportional to flow rate or, sorry, is it directly proportional to flow rate or indirectly proportional to flow rate?
Directly proportional.
Yeah, In the book, it calls it linear proportional, so directly proportional fluid. So it is a calibrated swing within the housing. It just looks like the back of a boat. Calibrated so it is proportional to the fuel flow. We had two types of variable area flow meters. I've said one of them. What's the name of the other types? Orifice and
plug flow meter.
Plug flow, yeah. So again, the plug flow, as it sounds, it's a tapered plug. The more that moves out the way, the bigger the gap where it was. Again, quite a simple setup there. Good. What I might highlight for you guys, just for your notes. Again, that type of transmitter is fitted with a copper coil on the spring for correct temperature variation. So copper, excuse me, also the heat temperature of the fuel will expand and contract, so it's designed to compensate for those variations and also for specific gravity. Now, does anybody remember the formula for variable area flow meters? If you do, you're doing very well. If you're not looking at your books. It was mass flow equals something multiplied by square root.
Area of orifice multiply the square root of pressure difference across the orifice.
Good, yeah. That's it, and that's for the variable area type. So mass flow equals the area multiplied by square root of the pressure differential. Good. Okay, that's just specific to the variable type ones. The helical vane flow meter, the one with impeller in it, okay, it was used to measure what type of flow rate?
High flow rate.
Yeah, high flow rate. And what was the purpose of the vanes inside it?
Prevent the false reading.
Good.
And
okay.
State the flow. Or direct the flow to
that's
the.
Right. Yeah. Good. And how do we get an electrical signal from an impeller? From that type.
From magnetic insert in the electrical connector.
Yeah. You got a magnet. Is it in the connector or is it an impeller?
Impeller. The magnet is in the impeller.
In the impeller. Yeah. Good. Okay. Which type of flow meter output or types of flow is not commonly or very rarely used? What type of flow is not very rarely used? Is very rarely used, I should say.
Velocity.
Yeah, velocity flow. Yeah, good. And what's the most common type?
Mass flow.
Mass flow, good. And again, what are the units?
Kilogram per second and pound per minute.
That's right. Good. If I said to you, what does delta P mean?
In USA?
Delta P.
Pressure difference.
Pressure difference, yeah. I've said to you delta T, what would that mean?
Temperature difference.
Yeah, I've said delta V, or delta N actually, not V, because V can mean a lot of things. Delta N.
Frequency difference.
Frequency, yes, speed, that sort of thing. Yeah, good. Okay. Right, I think we'll do, right, that's close enough for the moment. Let's go for another break. Come back about 1/2 past. Well, might have to be 1/4 past for you guys. And then we'll finish a bit more revision to about 4 o'clock, and that will do for today. Okay, so come back in about 20 minutes, guys, and we'll go for a bit more recap. We also find one in the CVG system as well.
Stating bands?
No. What was that electrical component? 4 letters.
LVDT.
LVDT.
Yeah, LVDT, linear variable differential, in this case, a transformer, okay? That'll send an error signal The gimbal, if it's out of balance, if it sends a signal, it'll give an error signal to the potentiometer at a specific rate, which will move your gauge. All right. Inlet pressure is sensed by what type of sensor? A standard pressure sensor, maybe P1, be sensed by what type of pressure sensor?
Single period type.
Yeah, single pitot probe. Good. Okay, go. Always good there. When is for EPR? When is the highest EPR available or achievable? So the ratio between exhaust gas outlet and exhaust gas inlet is its highest at when would it be highest? The ratio between the two.
In full throttle setting.
Say again?
In full throttle.
Full feather.
Full throttle, yeah.
Full throttle setting.
Full throttle. Yeah. Would that be full throttle in the air or full throttle on the ground?
Ground.
Yeah, full throttle on the ground. It's static when the aircraft's not moving. When the aircraft's not moving, you'll get the highest ratio available. Okay. Okay, doke. Going back to pyrometers, what was the improvement on a pyrometer system to prevent carbon formation buildup?
Hole.
Yeah, modification of a bleed of air to pass around the nozzles, or extension. Good. What was the name of the cell that converted light energy into electrical energy?
Photovoltaic.
Yeah, photovoltaic. Thermocouples, basic thermocouples are only good up to what temperature range?
Up to nearly 15,000.
No, that'd be quite high. 15,000 would be quite high.
Yeah,
No.
sorry, 11.
1100, yeah, 1100, yeah. The 15 you're thinking about is the 1500, which turbine temperatures can go up to.
Mm-hmm.
Yeah. What I'll mention there as well as the thermocouples, you might find that some blades, as well as pyrometers, should say, some blades, the thermocouples are actually embedded into some of the turbine blades themselves. We still have them on the Rolls-Royce engines, including NGVs, may have nickel coils built into the actual structure. So the actual sensors inbuilt into the NGVs as well. Very hard to replace, unfortunately. Okay, when we're averaging temperature readings, some systems will sample temperature reading from the thermocouples at frequent intervals. So at fatigue levels, now the fatigue levels is at high cycle fatigue or low cycle fatigue can be determined.
Low?
Yeah, low cycle fatigue. Yeah, the engine starts, stays on for a while. It's not in and out or off and on like a piston engine. Thermocouple output will also be passed to what other component? In case of an accident. So the thermocouple will get a temperature reading. It will send it to indication, maybe the fuel control, but also send the signal or the reading to this other component, which is what? Which is used in case of an accident. Yeah, the ADR, yeah, the aircraft data recorder, yeah. Okay, what resistor compensates for differences in resistance in the thermometry system. So what resistor compensates or calibrates for changes in or differences in resistance within the system? Keywords calibration. Say again?
Trim resistor.
Yeah, trim resistor, yeah. That accounts for changing the actual materials, the properties of materials being used, or from the thermocouples, the harnesses, etc. So, okay, the change in resistance, although it's the exact same part number, they will have slight change in resistance. So, a trim resistor accounts for that and works for calibration. So, the name of the resistor which works for indication, make sure that the gauges indicate all the same, is which one? So the trim resistor, and what's the other one that does indication? So the trim resistor and the one for the gauges for indication, which was
Ballast resistor.
Yeah, ballast resistor. Good, thank you. Okay, so that will give thrust all indications read at the same temperature. So ballast resistor for balancing, balance the indication for the pilot. Okay. Right. If we disconnect an indicator, temperature indicator gauge, what will it read? If we disconnect an indicator gauge, temperature indicator gauge, what will it read? Yeah, local ambient temperature specific to that day. What is the T1 thermocouple normally made from?
Iron and constant.
Yeah, and constant. Good. Two types of thermocouple common in use are which one is very fast but not as accurate?
A rapid response.
Yeah, it sounds very rapid but not as accurate. Good. Right. What are normal thermocouples made from?
Nickel, chromium.
Yeah, and
nickel, aluminium.
yeah, so chromal and aluminum. Okay, so chromal is your nickel, chromium, and your aluminum is your nickel, aluminium. Now, just as one you want marking in books as well, the chromal one is the positive wire, and the aluminum one is the negative wire. I meant to mention that before break. So the chromal is positive, aluminum is negative. And they typically produce how much voltage? That's 600 degrees C. How much
25.
voltage? Yeah,
25
millivolts. Yeah, just a small amount of voltage. Good. Some engines, it is necessary to indicate direction of rotation. So how do we indicate the direction of rotation of a shaft? How would that be carried out? Or what would we use?
By putting phonic speed probe and phonic wheel in 90 degree.
Yeah, two speed probes at 90 degrees. Okay, good. If on a speed probe phonic wheel, if the sensor of the tooth, no, let's say this again. If the tooth has just gone past the sensor, what voltage will I get?
Max negative voltage.
Maximum, yeah, we're coming down the slope again, good. And if it the tooth just a way to come up to the sensor, what do we get?
Max positive voltage.
Yeah, If the sensor's directly opposite the tooth, what's that one?
Is 0 volt.
0 volts. And if the sensor's in between two teeth, what is that one?
0 volt.
0. Good, good, good. Okay. How many pole pieces are in a probe assembly for the speed probe?
Sorry?
How many poles are there in a speed probe sensor for the probe? A bit more?
3 pole.
2 probe.
Yeah. 3 pole pieces in a coil, yeah. And the spacing of the pole pieces are what in relation to the pitch of the teeth? Are they different or the same to the pitch?
Equal to the pitch.
Yeah, the same, just exactly the same, yeah. So if there's a tooth over it, the poles will be facing in line for me as well. Good. What was the gearing ratio for the tacho indicator?
10:1.
10 to 1, yeah. Okay, doke. What type of generator is a tacho generator?
3-phase.
3-phase, yeah.
Synchro
Common-
motor.
So that's for the tacho indicator. For the tacho generator, yeah, it's 3-phase, delta wound, also known as a type of animal.
Yeah, squirrel cage.
Yeah. The tacho indicator is also 3-phase. But what type of motor is it?
Synchro motor.
Synchromotor. Good. Good, good, good. So indications there. And give me some examples of the type of indicators you might find in the cockpit.
Rotational speed, EGT,
Yeah.
power,
Yeah.
oil and fuel pressure,
Yeah.
and oil and fuel temperature, fuel flow, vibration, torque, and engine control.
Good stuff. Good stuff. Okay, right, let's go back a little bit more. Going back into book 3. Okay. What information would you find attached to a flexible hose?
Serial number,
Yeah.
date of manufacture,
Uh-huh.
last checked,
Yeah. Yeah.
part number,
Random, yeah. Yeah,
and
that's good.
yeah,
Yeah, that'll do for now. Good. What should the resistance not exceed when carrying out any bonding tests?
excuse me,
What should the resistance be or not exceed, not be any more than when you do a bonding test?
3 volt,
No, resistance is not in voltage, is it?
sorry,
0.025.
Otherwise,
0.025.
yeah, 0.05 ohms. Remember, resistance always in ohms.
yeah,
Okay. At what direction will air pass through a cascade vane? Remember what a cascade vane is? Cascade.
45,
Sorry?
45,
Yeah, 45. That's it. Yeah, you've got your thrust reverser. So the thrust reverser cascade vanes are at 45 degrees. Okay. How long should the APU be left to run before putting it into the load state?
1,
Yeah, 1 minute, yeah. How long should the APU be left to run in the no load state before shutting down?
2 minutes,
2 minutes, good. How long should you wait before you work on an APU ignition system?
3 minutes,
3 minutes. Once you've disconnected stuff, don't just wait 3 minutes to go in there. Make sure you disconnect it correctly. All right. At what speed percentage will the APU automatically shut down?
is over 110% RPM.
Good.
Yeah.
Where does an APU get its air supply from?
From air intake.
Yeah, basically a door that opens inside the fuselage, wherever that is. It could be the tail, the side, wherever, and that'll allow you to suck some air in. Good. Ba, 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 ba. That's okay, leave that one. Happy with that one. Done that one, that's good. Done that. Some usual ones there. I'll just try and find another one for you. That's a bit different. Oh yeah, just make sure. Thrust struts on side-mounted engines are usually fitted where? Thrust struts.
Back of the engine.
Not the back, no.
You mean shrouds?
The thrust strut, yeah, thrust strut. It's fitted to a side-mounted engine, but where is it placed? Where is it between?
Between fuselage and the engine.
Yeah, it is there. Well, what about the other mounts? What about the other mounts? Is it in front of the front one? Behind the back one? Or in between the front and rear?
In between front and rear.
Front, yeah.
Yeah, and what does it do then? What does it help?
It is
It used to transmit thrust from the engine main attachment mounting in pylon.
Yes, not the pylons, it's side mounted. It just spreads the load evenly. Helps to spread the load between the front and
spread
rear.
the thrust load evenly.
Okay, good. Good. All is good there. Okay. Right, what load do forward mounts generally carry? What type of loads do forward mounts generally carry? They carry thrust and also
carry thrust and vertical and side load.
Yeah, good. Vertical and side loads. Yeah. And what about the rear mounts?
Excuse me?
And what about the rear mounts, the aft mounts? They restrain the engine movement.
They restrain the engine.
What directions?
Move in all directions except forward and aft.
Yeah, forward and aft. Good. Vertical and side loads. Well, sorry, not forward and aft, but vertical and side loads. Yeah. All right. After an automatic shutdown of an APU, what would you do next?
We'll switch off
Yeah, just switch the switch off. Yeah, that way, if you switch it off, there's no power going to the APU in case it decides to try and start itself for some bizarre reason. Okay. Good. Done that one. Done that one. Done that one. When is the APU bleed valve ready for load? At what percentage?
90?
Yeah,
95? Yeah, 95.
Yeah, good. Okay. If EGT increases to 650 degrees C, what happens? If EGT increases to 650 degrees, what happens?
Control thermostat.
Thermostat opens.
Thermostat opens, yeah, good. And then what happens?
The valve modulates towards the closed position.
Yeah, good.
And reduce the load and ends.
Yeah, and reduces the fuel supply. Yeah, good.
Yeah.
If it doesn't, though, it gets to 695 degrees, what happens then? So if it doesn't do it there, but it gets to 695 degrees, it's the last chance, really.
Bleed valve closes.
Yeah, bleed valve will be closed, yeah. Your over temp switch will be energized, yeah. What's the number for the air ground relay?
R38.
Yeah, good. Thank you. R38. Yeah. Good, good, good. Okay. At what percentage RPM during a start cycle will the APU de-energize the starter circuit?
95%.
Not before that one.
35.
45.
Yeah, 35%. Good. 35%. All right. What valve will open at approximately 10% RPM?
Solenoid, fuel solenoid valve.
Yeah, fuel solenoid. Good. Good, good, good. So the oil temperature switch in an APU lubrication system is set to what temperature?
To 225 degree Fahrenheit.
Yeah. Or for Celsius?
125 degree. 124.
Yeah. Yeah, 124. Good. And when does the pressure relief valve open? At what PSI?
55.
No, a bit higher.
Closes. Oh,
When does the system pressure relief valve open?
90 psi.
Yeah, good. 90 psi. Good. Okay. That's one done. That one's done. And where would you find? Where would you get fuel for the APU? Where is it supplied from?
Main tank. One of the tank from the aircraft.
Yeah, that's good. Okay. Okay, that one's okay there. All right. Going back to free turbine overspeed. At what percentage RPM would it shut the engine down if a shaft broke? So let's say that the NF or the NF pulse probe sends an overspeed of the free turbine because it's broken, and it reaches a percentage. What was the percentage?
120.
120. Yeah, good. Good, good, good. Right, which lever will independently move the blades of the rotor?
Cyclic.
Good, yes, cyclic. Yeah, because cyclic can go forward, back, left, and right. So it will only change the pitch of one rotor blade. The collective does the whole thing, yeah. And what was the terminology we used when, if there was no anticipator fitted, we went to increase the pitch, which decreases the RPM. What was that name given? When you lose a little bit of good static drift. Good. Good, good, good. And what are the three types of couplings used in gas turbine engines?
Corbic, gimbal, and splint.
Good, good, good. Which one has the flexible joins? Which one has the flexible joins?
Gimbal.
Gimbal, yeah, good.
Gimbal,
Thank you.
yeah.
All right. What valve will be activated by the FAFC, the fuel authority fuel control unit, if there's a seized LP shaft?
Pressurizing shut-off and dump valve.
Good, yeah, pressure raising, shut off and dump valve, good. On the mechanical LP shaft disconnect system, how many turns does the nut turn to initiate the shutdown?
3/4.
3/4, good. On which type of engine, fixed turbine or free turbine, would you find dual lever controls?
Is in free turbine.
Free turbine, yeah. And the same sort of engine on a power lever. When you go into the beta range, what is the angle of attack you can change the blade pitch from?
Positive 20 and negative 20.
Good.
Positive 20 to negative 20.
Good, good, good. Where is the throttle quadrant?
Mm. Thrust lever.
The lever's attached to it, but where is the throttle quadrant?
Center pedestal.
Yeah, center pedestal, yeah, between the pilot and the co-pilot, where your throttle levers, your HP cocks, and all that sort of attached to as well. Just do a different one in there, don't worry. HP cock, start lever, has 3 positions. Might have 2, but something says 3. Which were?
Fuel cutoff.
Yeah.
Start position and run.
Yeah. And my good old favourite, what are the 4 requirements for control systems?
Accurate, positive, reliable, effective.
Yep. Effective. Good, good, good. Easy peasy, lemon squeezy. Okay. Turboprop engines are split into 2 categories, which are
Free and fixed and power turbine.
good, good. And the last one, what is equivalent shaft horsepower formula?
Shaft horsepower plus thrust, jet thrust.
Good. Good, good, good. That's a quick recap there, book 3, and what we've covered today so far. That's probably close enough at the moment. Right, folks, any questions about any of today's stuff you want to go through?
Good night.
That's the best bit. Yeah, good night. Okay, guys. Right, well, so see you tomorrow. Thank you very much again, and we'll continue.